If you could float, weightless and still, at the very edge of our solar system, the first thing you would notice is not the planets, not the sun, but the quiet. A quiet so deep and so complete that it feels almost like a substance, like a soft, dark blanket wrapped around everything. Out here, the sun is not the blazing disk we know from a summer afternoon. It is a distant point of light, brighter than the other stars, certainly, but a point of light nonetheless. You could cover it with the tip of your thumb if you stretched out your arm. And the warmth you might expect from it, that familiar feeling of sunshine on your skin, is almost entirely absent. Out here, the temperature is a cold so profound it is hard for the mind to hold on to, a cold that sits just a few degrees above the absolute still point where all motion of atoms nearly ceases. This is the neighborhood of our home, the solar system, seen from its outermost quiet edges. And tonight, we are going to drift slowly through it, starting from this faraway, peaceful place, and moving gently inward, step by soft step. Let's begin with the shape of this neighborhood, the basic layout of our cosmic home. The solar system is, in its simplest form, a single star, and everything that is held in orbit around it by the patient, steady pull of gravity. That star is our sun. Around the sun, like ripples spreading out from a stone, dropped into a still pond, circles a family of worlds. There are 8 major planets in this family. Some are small and made of rock, huddled close to the central fire. Others are vast and made mostly of gas and liquid, swirling with slow storms and wearing rings of ice and dust. Beyond them lies a scattering of smaller, frozen worlds, and beyond even those, a vast cloud of icy fragments stretching out into the darkness. All of it, every planet, every moon, every speck of dust, is bound together by the sun's gravity, a silent, invisible tether that keeps everything moving in its calm, predictable paths. Think of the solar system not as a crowded, busy place, but as a mostly empty, quiet expanse. The distances between things are so large that our everyday words for size and space start to lose their meaning. Imagine the Earth, our home planet, as a small, smooth blue marble. On this same scale, the sun would be a glowing sphere about 2 feet across, sitting some 220 feet away. That's more than half a football field of mostly nothing. The moon, our closest neighbor, would be a tiny pebble orbiting just a few inches from our blue marble. And Mars, the next planet out, would be another, slightly smaller pebble, sometimes coming as close as 150 feet from us, and sometimes drifting almost 1,000 feet away. These are the distances in our own backyard, the part of the solar system we consider crowded. The space between objects is vast, and the objects themselves are, compared to that space, almost unbelievably small. All that emptiness is not a void to be feared. It is a soft, dark ocean of stillness, and we are just tiny boats drifting on its surface. As we begin our slow, unhurried tour, picture yourself not in a rushing spaceship, but simply floating, a quiet observer with no need to hurry. There is no schedule out here, no ticking clock. A year on one world is a fraction of a year on another. The planets move at their own pace, in their own time. Jupiter, huge and slow, takes about 12 Earth years to complete one loop around the Sun. Neptune, far out in the dim, cold reaches, takes about 165 Earth years. A single orbit there is longer than a human lifetime. Out here, time itself seems to stretch and slow down. We will match that pace, we will take our time, looking at each world, each collection of dust and ice, with the same gentle, patient attention. There will be no tests, nothing you need to memorize. You don't have to remember the names or the numbers. You can let them wash over you like soft waves on a shore, and if you drift off before we reach the end, that's perfectly fine. The journey will wait for you. The solar system has been here for more than 4.5 billion years. It is in no rush, and neither are we. So let's start our gentle drift inward from this quiet edge, this place of faint light and deep cold. The outermost boundary of our sun's influence is thought to be a vast, spherical cloud of icy bodies called the Oort cloud. We will visit it properly later, but for now, just know that it is so far away that the distance is measured not in miles, but in the time it takes light to travel. Light, which can circle the Earth more than 7 times in a single second, takes many hours, perhaps even a full day, to travel from the Sun to this distant shell. Out here, the Sun's gravitational grip is so weak, so gentle, that these icy fragments are only loosely bound. A passing star, even one moving by at a distance we can barely comprehend, can nudge them, sending some of them on long, slow journeys toward the inner system. This is the threshold, the place where our solar system whispers its last hello to deep space. From this almost unthinkable distance, if you could see the whole system at once, it would look like a tiny, bright jewel box floating in a vast, dark room. The Sun, that central anchor, would be the brightest jewel, but still just a single point. Around it, almost invisible, would be the faint, gossamer rings of dust and ice. The planets themselves would be lost in the glare, too small and too dim to see with the naked eye from this far out. The whole thing, this entire collection of worlds and light and energy, is just one small neighborhood in a much larger city, the Milky Way galaxy. The galaxy contains hundreds of billions of other stars, and each one of those stars might have its own family of worlds, its own quiet, empty neighborhood of space. We are one of many, a single calm note in a long, slow symphony. Moving inward just a little, we come to a region that feels slightly more defined, a disk of icy dark objects called the Kuiper Belt. Here, the objects are still small, frozen leftovers from the solar system's birth, but they are closer together than the Oort cloud's far-flung specks. This is where the dwarf planet Pluto lives, a world of mountains made of water ice and plains of frozen nitrogen. It's a quiet, distant outpost, receiving so little sunlight that from its surface the Sun would appear as an exceptionally bright star, nothing more. The temperature here hovers around -375 degrees Fahrenheit, a cold so intense that the very air we breathe would freeze solid and fall as snow. But there is no air to speak of, just a thin, temporary wisp of atmosphere that comes and goes with Pluto's slow, 248-year orbit. The stillness here is perfect, unbroken. The only movement is the slow, stately dance of the moons around their parent worlds, and the silent, invisible fall of particles toward the Sun. As we continue our gentle inward drift, the spaces between worlds slowly begin to shrink, but only by comparison. We reach the realm of the ice giants, Uranus and Neptune. These are worlds of deep blue and green, colored by the methane in their atmospheres. They are huge by earthly standards, but still, the distance between them and us, or between them and each other, is staggering. Billions of miles of quiet, dark space. If you were to stand on one of Neptune's moons, looking up at the planet's soft blue disk, the other ice giant, Uranus, would be nowhere to be seen, just another faint point of light lost among thousands of others. The emptiness is still the dominant feature. The planets are not like cars on a busy highway. They are like solitary ships on a vast, calm ocean, passing so far apart that they never even see each other's lights. This is the defining truth of our cosmic home. It is a place of immense, tranquil separation, and in that separation, there is a profound kind of peace. There is no noise, no collision, no chaos, just objects moving on their appointed paths, held by an invisible hand, in a silence that has lasted for eons. Now, let's move past the ice giants and into a region that serves as a kind of boundary line between the outer and inner parts of our neighborhood. This is the asteroid belt, a wide, flat ring of rocky rubble orbiting between Mars and Jupiter. When people first imagine an asteroid belt, they often picture a dense, dangerous field of tumbling boulders, something a spaceship would have to swerve and dodge through. The reality is much calmer, much more gentle. The asteroid belt is mostly empty space. If you were to stand on one asteroid, the next one of any decent size would likely be millions of miles away, just a faint speck of light against the black. The total mass of all the rocks in the belt is only a small fraction of the mass of our own moon. They are not a wall, but a scattered collection of pebbles on a very large, dark floor. They are the leftover building blocks that never formed a planet, their quiet assembly interrupted by the powerful gravity of nearby Jupiter. And so they remain, a silent, drifting archive of the solar system's earliest days, patiently circling the sun. Moving even further inward, we begin to feel the sun not just as a point of light, but as a source of warmth. We are entering the realm of the rocky inner planets, Mars, Earth, Venus, and Mercury. These are worlds where a solid surface exists, where you could, in theory, stand and feel the ground beneath your feet. They are closer together than the outer worlds, but the spaces between them are still vast, still defined by emptiness. The average distance from Earth to Mars is about 140 million miles. A beam of light, the fastest thing in the universe, takes more than 12 minutes to cross that gap. A conversation sent by radio signal would have a 12-minute delay for a simple hello. The quiet persists, even here in the crowded part of the solar system. The sun is the dominant presence now, its light washing over everything, its warmth bringing a semblance of energy and change to these small, rocky shores. It is the hearth of our home, and we are slowly, gently moving toward it. But for a moment longer, let's stay with this feeling of the whole system, this wide-angle view of our quiet neighborhood. The sun holds it all together, its gravity reaching out invisibly in all directions, the master of a silent orchestra. Every planet, every moon, every ring particle and comet nucleus is moving in a slow, predictable curve around it, a curve that can be calculated millions of years into the future. There is a deep, orderly peace to it all. This is not a place of wild, unpredictable chaos. It is a place of steady, clockwork rhythms. Planets trace their elliptical paths, moons circle their planets. The whole system, the entire, vast, flat disk of it, is moving together through the galaxy, carrying us all on a grand, slow journey around the galactic center, a journey that takes about 230 million years to complete. We are all passengers on a quiet, stable ship, sailing through the dark. So as you lie here in the dark, let that sense of scale and stillness settle over you. The air in this room, the walls around you, the ground beneath the building, it's all part of one of those tiny, rocky inner planets. We are on that small blue marble, drifting silently through this immense, mostly empty space. And from this perspective, the things that can seem so large and urgent in the daytime, the worries, the to-do lists, the noise, might start to feel a little smaller, a little more distant. They are contained on this tiny, peaceful world. Outside, for billions and billions of miles in every direction, there is just quiet. There is just the soft, dark ocean of space and the slow, patient dance of the planets. And that quiet, that deep, cosmic stillness is the very thing we are going to drift through together. We will explore it, one gentle step at a time, on a tour that has no end and no test. You are already exactly where you need to be, lying comfortably, listening, floating at the edge of our solar system, ready to begin the slow, soft journey home. Now, before we drift among the planets themselves, let us ease back even further, to a time before the solar system existed at all, a time before the sun, before the earth, before any of the quiet worlds we will visit. To understand this neighborhood of ours, this calm, mostly empty space we now float through, it helps to know how it came to be. So let the story begin not with a bang, not with a flash, but with a cloud. A vast, slowly drifting cloud of gas and dust hanging in the dark of space, quiet and cold, about 4,600,000,000 years ago. Picture this cloud, if you can, not as something solid and dense like a storm cloud on a summer day, but as something far more spread out, far more diffuse. It was a collection of tiny particles, mostly hydrogen and helium, with a scattering of heavier elements, tiny grains of ice and rock and metal, all floating separately in the dark. The whole thing stretched across a region of space many times wider than our entire solar system is today. And it was cold, very cold. The atoms within it were barely moving, barely brushing against each other. It was a place of near-perfect stillness, a quiet gathering of the most basic ingredients. This enormous, gentle structure is what we call a solar nebula. The word nebula simply means cloud, a soft, hazy patch against the deeper black of space. And this particular nebula, our nebula, was about to begin a long, slow process of transformation that would eventually lead to everything we see around us in the sky tonight. For a long stretch of time, perhaps nothing much happened. The cloud simply hung there, balanced between its own inward pull and the outward push of what little warmth it held. Gravity, that same quiet force that now keeps the planets in their orbits, was already at work. Every single particle in that cloud, every atom and every grain of dust, exerted a tiny gravitational pull on every other particle. Individually, the pull was almost nothing, a whisper too faint to notice, but across the vastness of the nebula, all those whispers added up. The combined gravity of the entire cloud began to draw material inward, toward the center of the mass. Slowly, very slowly, the cloud started to contract. It was not a sudden collapse, not a violent rush. It was more like a soft, inward sigh, a gentle settling that took place over millions of years. As the cloud contracted, something else began to happen, something you might have seen in a much smaller way in everyday life. Think of a figure skater spinning on the ice. When the skater pulls their arms in close to their body, their spin gets faster. The same rule applies to a collapsing cloud in space. As the solar nebula drew itself inward, as its material fell toward the center, the whole cloud began to spin. Very slowly at first, but as the contraction continued, the spin quickened. This spinning changed the shape of the cloud. Instead of a roughly spherical, ball-shaped puff of gas and dust, the nebula began to flatten out into a rotating disk. It became like a giant, spinning pancake of material, thicker in the middle and thinner at the edges. This shape, a flat disk with a bulge at the center, is a common pattern we see throughout the universe, from the rings of Saturn to the spiral arms of galaxies. It is what happens when gravity and spin work together on a loose collection of stuff. If you have ever watched someone spin pizza dough, tossing it into the air and watching it spread out into a wide, thin circle, you have seen a small version of this very process. The solar nebula was, in essence, spinning itself into a disk. Most of the material in the nebula, the vast majority of it, gathered at the very center of this disk. Gravity pulled it inward, packing it tighter and tighter, squeezing it into a smaller and smaller space. As the material compressed, it began to heat up. Think of how a bicycle pump gets warm when you press down on the handle, compressing the air inside. The same principle was at work at the center of the nebula, but on a scale almost beyond comprehension. The central ball of gas grew denser and denser, hotter and hotter. Over time, it became a glowing, churning sphere of mostly hydrogen, a kind of protostar, a star that was not yet fully lit. The pressure and the heat kept building, until the very center of this ball reached a temperature of millions of degrees. At that point, something fundamental changed. The hydrogen atoms at the core were no longer just bouncing off each other. They were being slammed together with such force that they began to fuse. Hydrogen atoms combined to form helium atoms, and each time this happened, a tiny amount of energy was released. Multiply that tiny release by trillions and trillions and trillions of times, and you have the birth of a star. This process, the fusing of lighter atoms into heavier ones, is called nuclear fusion. It is the engine that powers every star in the sky. And the moment fusion began in the heart of our cloud, the sun was born. It turned on, flooding the surrounding disk with light and heat for the first time. But the story does not end with the sun. The newborn star contained about 99.8% of all the material in the original nebula, but not all of it. The rest, that tiny fraction of leftover gas and dust, remained in the spinning disk around the young sun. And this leftover material, this thin haze of cosmic debris, is what eventually became everything else. The planets, the moons, the asteroids and the comets. All of it was formed from the same thin, rotating cloud of leftovers. Think of that for a moment. Every world we will visit, every rocky surface and swirling gas giant, every ring of ice and belt of stone, is made from the same raw ingredients, the same ancient dust that once swirled quietly around the newborn sun. The process of building planets from this disk was a slow, patient one. At first, the dust grains in the disk were microscopic, smaller than the particles in a puff of smoke. But over time, through gentle collisions and the subtle pull of static electricity, these tiny grains began to stick together. A grain of dust would bump into another grain of dust, and they would cling. Then that slightly larger speck would bump into another and another. Slowly, particle by particle, these specks grew into small, pebble-sized chunks. The pebbles grew into boulders. The boulders grew into larger bodies, sometimes called planetesimals, a word that simply means the small, building block pieces that can eventually form a planet. This process, this gentle, steady clumping together of material, is called accretion. It was not a violent, chaotic process, at least not most of the time. It was more like a slow, patient gathering, a steady sweeping up of the material in the disk over millions and millions of years. In the inner part of the solar system, close to the young sun, the heat was intense. The lighter materials like water ice and methane ice and gases like hydrogen and helium could not survive as solids. They were boiled away, pushed outward by the sun's energy. So the planetesimals that formed in the inner region were made mostly of heavier, rockier stuff, things like iron, nickel, and silicon. These rocky chunks collided and merged, slowly building up the four inner planets: Mercury, Venus, Earth, and Mars. They became small, dense, solid worlds, with hard surfaces you could stand on. Farther out, beyond what we now call the asteroid belt, the sun's heat was much weaker. Here, the temperatures were low enough for ices to exist. Water ice, methane ice, ammonia ice, these frozen materials were abundant in the outer disk. The planetesimals out here were made not just of rock, but of vast quantities of ice. And because there was so much more solid material available to them, these outer worlds grew much larger than their inner rocky siblings. They became the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. Their strong gravity, once they grew large enough, was able to sweep up the remaining hydrogen and helium gas from the disk, wrapping themselves in thick, deep atmospheres that have no solid surface to this day. Not all of the material became planets. In the space between Mars and Jupiter, the powerful gravity of the forming Jupiter stirred up the planetesimals, preventing them from ever clumping together into a single world. This region remained a scattered belt of rocky leftovers, the asteroid belt, a quiet, failed planet that serves as a reminder of what might have been. And far beyond Neptune, the icy leftovers remained, too, forming a vast, sparse disk called the Kuiper Belt, and even further out, a huge spherical shell called the Oort cloud. These are the frozen, unchanged building blocks, the pieces that never found a planet to join. They have been drifting out there, in the quiet and the cold, ever since. There is one part of this story that remains, even now, not fully understood, and it is a peaceful kind of not knowing, a gentle mystery that sits at the very beginning of everything. What caused the original cloud, that vast, quiet solar nebula, to start its collapse in the first place? We know that it did. The evidence of what happened next is written in the rocks and the orbits and the very existence of our world. But the exact trigger, the specific event that pushed the cloud from a stable, floating mass into a contracting, spinning disk, is something we cannot point to with certainty. It may have been a nearby star exploding, its shockwave gently compressing the cloud as it passed. It may have been a subtle gravitational nudge from a passing star, a quiet hello that was just enough to disturb the balance. Or it may have been something else entirely, a process internal to the cloud itself that we have not yet puzzled out. We do not know, not for sure. And that is perfectly all right. The not knowing is part of the calm. It is a soft, open question at the edge of our story, a reminder that the universe does not owe us every answer. We can simply accept that the cloud began to fall together, and that from that falling, everything we are came to be. So now, as we drift in this quiet, familiar present, you carry the whole history with you, the air you breathe, the ground beneath you, the very atoms in your body were all forged in this long, slow process. The hydrogen in the water that makes up most of you was there in the original nebula. The heavier elements, the carbon, the oxygen, the calcium in your bones, were made even earlier, in the cores of long-dead stars that lived and died before our sun was even a thought. You are made of stardust, a phrase that is as true as it is soft. And the story of how that stardust gathered into a world, our small blue marble, is a story of infinite patience, no rush, no deadline, just gravity and time and a slow, steady drifting toward order. Let your mind rest on that image for a while. The great spinning disk, glowing softly at its center with the light of the new sun, the tiny, sticky grains of dust, floating in the dark, gently touching and clinging and building, the slow, patient sweep of the planets as they cleared their paths around the star. It is a process that is still happening, in a sense. The solar system is not frozen in time. The planets still orbit, the sun still fuses, the asteroids still drift, and far, far out, at the very edges of the sun's influence, the icy remnants of that ancient disk still float in their slow, cold loops. The story is not over, it just continues, quietly, without hurry, in the vast, calm dark. From this deep, deep history, we can now begin to turn our attention to the thing that started it all, the anchor that holds it all together, the quiet heart of our neighborhood, the sun. Let that thought settle. The sun, our star, is waiting for us in the quiet, and we will drift toward it, slowly, gently, in our own time. So let us drift now, slowly and gently, toward the center of everything, toward the anchor that holds the whole quiet neighborhood together, the sun. It is the reason the planets exist. It is the source of almost all the light and warmth in the solar system. And it is so large, so overwhelmingly massive, that it shapes the very space around it. The sun is not just the most important object in our cosmic home. In many ways, the sun is the solar system, and everything else, the planets, the moons, the asteroids, the comets, all of it, is just the leftover dust and debris from its formation. When we talk about the sun's size and mass, the numbers can feel hard to grasp, but we can approach them gently, letting them settle into the mind like a soft, slow wave. The sun contains about 99.8% of all the mass in the entire solar system. Think of that for a moment. Every planet, every moon, every asteroid in the belt, every icy fragment in the Kuiper Belt, and every distant speck in the Oort cloud, all of it combined makes up just 0.2% of the mass of our neighborhood. The sun is everything else. If you could gather up Jupiter, which is itself more massive than all the other planets put together, and add to it Saturn and Uranus and Neptune and Earth and all the rest, the sun would still outweigh that combined pile by a factor of more than 700. It is the great, heavy anchor around which everything else gently, quietly, patiently turns. This immense mass is what generates the sun's gravity, the invisible tether that holds the planets in their orbits. Without the sun's gravity, every planet would simply fly off in a straight line into the dark, cold space between the stars. But instead they curve, they loop, they follow the slow, predictable paths that gravity has carved for them. The Earth, for instance, is moving at about 67,000 miles per hour around the sun, a speed that is hard to feel from down here, but it is falling, always falling, toward the sun. It just keeps missing. That is what an orbit is, a continuous fall where the object never quite hits the ground. And the sun's gravity, that gentle, persistent pull, is what turns a straight flight into a long, quiet curve that takes a year to complete. But what is the sun itself? What is it made of, and what is happening inside it that makes it shine? The sun is a star, a word that means a ball of mostly hydrogen and helium gas, held together by its own gravity, with a core so hot and dense that atoms are squeezed together, fusing into heavier atoms. This process, the one we touched on when we talked about the birth of the solar system, is the engine of the sun. It is called nuclear fusion, and it has been running steadily and quietly for about 4,600,000,000 years. Let us take a slow, gentle look at how this works. At the very center of the sun, the core, the temperature is about 27 million degrees Fahrenheit. The pressure is crushing, more than 200 billion times the pressure of Earth's atmosphere at sea level. Under these conditions, the atoms are not whole atoms in the way we normally think of them. They are stripped down to their central pieces, their nuclei. The most common atom in the sun is hydrogen, which in its simplest form consists of a single proton. In the core, these protons are flying around at incredible speeds, and the pressure squeezes them so close together that they can collide and stick. When four hydrogen nuclei, four protons, fuse together through a series of steps, they form one helium nucleus. And here is the key detail. A helium nucleus is ever so slightly less massive than the four protons that went into making it. That tiny bit of missing mass is converted into energy, into light and heat, according to the quiet, well-established rule of nature that says mass and energy are two sides of the same coin. Each individual reaction releases only a vanishingly small flicker of energy. But the sun is so vast and contains so much hydrogen that every single second, about 600 million tons of hydrogen are fused into helium, and from that, about 4 million tons of mass are converted into pure energy, every second, for billions of years. That is the quiet, steady, unimaginably powerful furnace at the heart of our sun. The energy released in the core does not simply shoot out into space all at once. It begins a long, slow journey outward, a journey that is so slow, so indirect, that the numbers can help us appreciate the quiet patience of the sun. The light that is generated in the core, the photons, the tiny packets of energy, spend tens of thousands of years, and sometimes hundreds of thousands of years, working their way from the core to the surface. This is because the interior of the sun is incredibly dense. The photons are constantly being absorbed and re-emitted, bounced and scattered by the densely packed particles in the sun's interior. They take a random, zigzag path, a long, slow, drunken walk toward the outside. The sunlight that warms your face on a summer afternoon was generated in the core of the sun long before modern humans walked the earth. It has been struggling outward for tens of thousands of years, and then, once it reaches the surface, it makes the final journey across space to us in just about 8 minutes. That contrast between the long, slow crawl inside the sun and the quick, straight flight through space is a soft, gentle reminder of the vast scales involved, of the deep patience built into the fabric of everything. The surface from which the light finally escapes into space is not a solid surface like the ground. It is simply the layer where the gas becomes thin enough, clear enough, that light can fly free without being immediately absorbed again. This visible layer, the part of the sun we can see, is called the photosphere. The word means sphere of light. The photosphere has a temperature of about 10,000 degrees Fahrenheit. It is not smooth and featureless. It has a kind of texture, a granular pattern of bright cells surrounded by darker edges, like the surface of a gently simmering pot of liquid. These granules are the tops of columns of hot gas rising from below, bringing heat to the surface, cooling slightly, and then sinking back down. The whole visible surface of the sun is constantly, slowly, and gently churning, a soft, rolling boil of plasma that gives the sun a quiet, living texture. There are also dark spots on the photosphere, called sunspots, which are areas where strong magnetic fields have cooled the local region slightly, making it appear darker by contrast. Sunspots come and go in a gentle cycle that lasts about 11 years, a slow, rhythmic breathing of the sun's magnetic field. Above the photosphere lies a layer of the sun's atmosphere that is, in its own quiet way, one of the long-standing mysteries of our solar system. This layer is called the corona. The corona is the sun's outer atmosphere, a faint, wispy halo of plasma that extends millions of miles into space. It is normally invisible to us, drowned out by the glare of the photosphere, but during a total solar eclipse, when the moon blocks the bright disk, the corona becomes visible as a soft, pearly, shimmering crown around the dark moon. And here is the gentle puzzle. The corona is much, much hotter than the surface below it. While the photosphere is about 10,000 degrees Fahrenheit, the corona can reach temperatures of several million degrees. This seems to go against common sense. If you stand farther from a fire, you expect it to be cooler, not hotter. But the corona is far hotter than the visible surface of the sun itself. The exact reason for this remains an open question in science. The leading ideas involve the sun's complex magnetic fields, which twist and snap and release energy into the corona, heating it up in a way that we are still working to fully understand. This is not a gap to be anxious about. It is just a quiet mystery, a reminder that even our nearest star, the anchor of our whole neighborhood, still holds questions we have not yet answered. The not knowing is part of the calm. The sun shines on, steady and warm, whether we understand every detail of its atmosphere or not. The corona is also the source of the solar wind, a constant, gentle outward flow of charged particles streaming from the sun in all directions. This solar wind blows past all the planets, filling the solar system with a thin, invisible breeze of protons and electrons. It is what shapes the tails of comets, pushing them always away from the sun. It is what creates the auroras, the northern and southern lights, when those particles are funneled down by Earth's magnetic field and strike the upper atmosphere, making it glow with soft curtains of green and pink and purple light. The solar wind extends far past the orbit of Pluto, creating a kind of bubble around our whole solar system, a region called the heliosphere. The heliosphere is the realm of the sun's influence, the space where the solar wind is still pushing outward against the thin, diffuse material between the stars. Where that solar wind finally fades and gives way to interstellar space is another one of those gentle, quiet boundaries, a soft, distant edge to our home. As we float here, at a safe, imagined distance, looking at the sun with a calm and steady gaze, let us think again about its size. The sun is about 865,000 miles across, a number that is hard to picture. If the sun were a hollow ball and you were to place Earth inside it, you could fit more than 1 million Earths inside the sun's volume. It is so large that it contains nearly all the light and heat in the neighborhood. The planets, the moons, the far-off icy fragments, they do not generate their own significant warmth. They only catch and reflect what the sun gives them. The Earth, for example, receives only about 1/2 of 1/1000th of the sun's total energy output. And yet that tiny, tiny fraction is enough to drive every wind, every wave, every growing plant, and every quiet, living process on our world. The sun is a generous, steady, and distant lamp, hanging in the dark, giving away its light freely and constantly to the quiet worlds that circle it. And that circle, that orbit, is the final, gentle thought for now. The sun is not fixed, not rigidly locked in place. It moves too. The sun orbits the center of the Milky Way galaxy, carrying the entire solar system with it on a long, slow loop that takes about 230 million years to complete. So everything is moving. The sun moves around the galaxy, the planets move around the sun, the moons move around the planets. It is a cascade of slow, steady, nested motion, a gentle clockwork of orbits within orbits, and at the heart of it all, holding it all together by the quiet, invisible force of its own weight, is the sun, our star, the anchor. From here, From the Sun, we can now begin our slow outward drift, visiting each of the quiet worlds that circle it. We will start with the innermost planets, the small, rocky bodies that huddle closest to the fire, the worlds of extreme heat and extreme cold, the worlds of Mercury and Venus. Leaving the Sun now, we begin our slow, gentle drift outward. The first world we encounter on this quiet journey is also the smallest, and the one that lives closest to the central fire, Mercury. It is a tiny, rocky planet, a dense ball of iron and stone, barely more than 3,000 miles across. To give you a sense of its size, Mercury is only about 1/3 the width of Earth, and it is actually smaller than some of the moons that orbit other planets. Jupiter's moon Ganymede and Saturn's moon Titan are both larger than Mercury. It is the smallest of the 8 planets, a modest, quiet little world that has been circling the Sun for the same 4,600,000,000 years as everything else. Mercury orbits the Sun at an average distance of about 36 million miles. That is close, cosmically speaking. So close that from the surface of Mercury, the Sun would appear more than 3 times larger in the sky than it does from Earth. It would be an enormous, blazing disk, dominating the daytime sky. But the sky on Mercury is not blue. It is not really a sky at all, in the way we think of it. Mercury has almost no atmosphere to speak of. There is a very, very thin layer of gas around it, what we call an exosphere, but it is so thin, so incredibly sparse, that it is practically a vacuum. The atoms in this exosphere are not held close by gravity in the way Earth's thick blanket of air is held. Instead, they are constantly being knocked off the surface by the solar wind, by impacts of tiny particles, and then drifting away into space. There is no air to breathe, no air to carry sound, and most importantly for the character of the planet, no air to hold in heat. This lack of atmosphere gives Mercury one of its most defining features, one of the things that makes it such a quiet, extreme little world. The temperatures on its surface swing wildly between day and night. Because there is no blanket of air to trap the Sun's warmth and spread it around, when the Sun shines on Mercury's surface, the temperature soars. It can reach about 800 degrees Fahrenheit, hot enough to melt lead. The ground itself becomes a scorched, sun-blasted landscape of rock and dust. But when the Sun sets, and the long night begins, all that heat simply radiates back out into space. There is no air to hold it in, no clouds to trap it. The temperature plunges, dropping all the way down to about -290 degrees Fahrenheit. That is cold enough to freeze methane, cold enough that the very rocks themselves must grow brittle and still. So on Mercury, a single spot on the surface can experience a temperature swing of more than 1,000 degrees between day and night. It is a world of extremes, a place where heat and cold exist side by side, separated only by the slow march of the Sun across the black, airless sky. Part of the reason for this long, slow march is the way Mercury spins on its axis. A day on Mercury, the time it takes for the Sun to return to the same spot in the sky, is not like a day on Earth. Mercury spins very slowly, and it also moves quite fast along its orbit, creating a strange, slow rhythm. A single solar day on Mercury, from one sunrise to the next, lasts about 176 Earth days. That is nearly half an Earth year, so if you were standing on Mercury, you would experience nearly 3 Earth months of continuous daylight, the Sun crawling very, very slowly across the sky, and then nearly 3 Earth months of continuous, freezing darkness. The Sun would seem almost to pause, to hesitate, before resuming its slow journey. It is a rhythm utterly different from our own, a slow, patient pulse that has been beating since the planet's formation. Mercury's surface, when we look at it up close, tells a story of a very old, very quiet world. It is heavily cratered, covered in the scars of ancient impacts from asteroids and comets. In this way, it looks a lot like our own moon, a similar landscape of gray, dusty plains and overlapping craters. There are no volcanoes erupting, no rivers flowing, no winds carving the rocks. the surface has remained largely unchanged for billions of years. Every crater, every crack, every ridge is a frozen record of the solar system's early, chaotic days, preserved in the stillness of this airless world. One of the most notable features on Mercury is the Caloris Basin, a huge impact crater, one of the largest in the entire solar system, stretching nearly 1,000 miles across. The impact that created it was so powerful that it sent shockwaves through the whole planet, creating a region of jumbled, chaotic terrain on the exact opposite side. But even that event, so long ago and so violent, is now just a quiet scar, a smooth, circular plain baking silently in the sun. Mercury also has a secret hidden deep inside it, a mystery that we only began to understand relatively recently. Despite its small size, Mercury is unusually dense. It has a very large iron core, proportionally much larger than the core of Earth. This iron core makes up about 85% of the planet's radius. Surrounding this huge metal heart is a relatively thin layer of rock, the mantle and crust. Why Mercury has such a large core is not known with absolute certainty. One idea is that Mercury was once a larger planet, and a giant collision in its distant past stripped away much of its outer rocky layers, leaving behind the dense, iron-rich body we see today. This is a quiet hypothesis, an open question that hangs gently over the little planet. The not knowing is, as always, part of the calm. Mercury does not mind that we do not fully understand it. It just continues its slow orbit, spinning and baking and freezing, as it has always done. Moving outward from Mercury, we drift past the quiet emptiness of space and encounter the next planet, the second rock from the Sun, Venus. If Mercury is a quiet, small, and extreme little world, Venus is something else entirely. It is a world of thick clouds and crushing pressure, a planet that, at first glance, seems like it should be a twin to Earth. Venus is very similar in size to our home planet. It has a diameter only slightly smaller than Earth's, and its mass is about 82% of Earth's mass. It is made of similar rocky materials, and it orbits not too much closer to the Sun, and yet the two planets could hardly be more different in their character and their environment. Venus is a place of slow, suffocating stillness, a world hidden beneath an unbroken layer of pale, yellowish clouds. Those clouds are the first thing we notice when we look at Venus, and they are the key to understanding why the planet is the way it is. The clouds of Venus are not made of water vapor like the clouds on Earth. They are made mostly of sulfuric acid, a corrosive, dense haze that completely shrouds the planet's surface from view. We cannot see the ground from space with ordinary light. The entire planet is wrapped in this soft, pale blanket of acidic droplets, reflecting sunlight and giving Venus its bright, calm appearance in the morning and evening sky. This is why Venus is so often called the evening star or the morning star, because its cloudy atmosphere reflects sunlight so well, making it the third brightest object in our sky after the sun and the moon. Below these sulfuric acid clouds lies an atmosphere that is almost unbelievably thick and heavy. The air on Venus is made almost entirely of carbon dioxide, with only trace amounts of other gases, and there is just so much of it. The atmospheric pressure at the surface of Venus is about 90 times the pressure at sea level on Earth. To feel that kind of pressure on Earth, you would have to dive more than half a mile beneath the surface of the ocean. Standing on the surface of Venus would feel like being at the bottom of a deep, dark, hot sea of gas. The air is so dense that it behaves almost more like a liquid than a gas in some ways. A gentle breeze on Venus, moving at just a few miles per hour, would push against you with the force of a strong ocean current on Earth, because the air itself is so thick and heavy. This thick, carbon dioxide-rich atmosphere is a perfect, powerful blanket. Sunlight can pass through the clouds and heat the surface, but the heat that the surface radiates back out cannot escape. The carbon dioxide traps it, holding it close, letting it build and build. This is the same process we call the greenhouse effect on Earth, but on Venus, it has run away to an extreme degree. The result is that Venus is the hottest planet in the entire solar system, even though it is not the closest to the Sun. The surface temperature on Venus, across the whole planet, day and night, pole and equator, is a steady, unchanging roughly 900 degrees Fahrenheit. That is hot enough to melt zinc, hot enough to melt lead. It is hotter than the day side of Mercury, the planet that is right next to the Sun. The thick blanket of air ensures that the temperature never drops, never varies, from one location to another or from day to night. It is a constant, smothering, planet-wide heat that has erased any trace of the gentle temperature swings we know on Earth. The surface of Venus, which we have only glimpsed through radar mapping that can pierce the clouds, is a strange and quiet landscape. It is relatively young, geologically speaking, with fewer craters than Mercury or the Moon. This suggests that the entire surface may have been resurfaced by vast outpourings of lava sometime in the last few 100 million years. There are broad, flat plains of volcanic rock, towering mountains, and strange, round features called coronae, which are thought to be places where hot material from the mantle welled up beneath the crust. The highest mountain on Venus, Maxwell Montes, rises to an altitude where the temperature is slightly cooler and the pressure is slightly less crushing, but it is still an utterly inhospitable place by earthly standards. There is another quiet, strange fact about Venus that sets it apart from the other planets, a detail that feels almost like a soft, slow puzzle. Venus spins backward. Most of the planets in the solar system spin on their axes in the same direction that they orbit the Sun. This is called prograde rotation. If you were looking down on the solar system from above the Sun's north pole, you would see most planets spinning counterclockwise. Venus, however, spins slowly clockwise. Its rotation is retrograde, and not only does it spin backward, it spins incredibly slowly. A single rotation of Venus on its axis takes about 243 Earth days. But Venus also orbits the Sun relatively quickly, taking about 225 Earth days to complete one loop. This combination, the very slow backward spin and the relatively short orbit, means that a day on Venus, the time from one sunrise to the next, lasts about 117 Earth days. That is actually shorter than its rotation period because of the way it is moving around the Sun. So a single day on Venus is longer than a Venusian year. The Sun rises in the west and sets in the east, and it takes so long to cross the sky that you could track its motion only with great patience, watching it inch, almost imperceptibly, along its slow path. Why does Venus spin backward? Like so many quiet mysteries in our solar system, the exact reason is not fully settled. One leading idea is that early in its history, Venus may have suffered a large collision, an impact so powerful that it flipped the planet's spin axis or simply reversed its rotation. Another idea is that the thick atmosphere itself, through complex interactions with the Sun's gravity over billions of years, may have slowed the planet's original spin and eventually tipped it into its current backward state. We do not know for certain. And that is perfectly all right. Venus, wrapped in its thick, pale clouds, keeps its secrets. It just continues its slow, backward rotation, baking quietly under its heavy blanket of air, drifting along its orbit, a world of silent, steady extremes. So here we have the two innermost planets, Mercury and Venus, our first two stops on the journey outward from the Sun. One is small, airless, and scarred, swinging wildly between searing heat and deep cold. The other is shrouded, heavy, and uniformly hot, spinning slowly backward under a crushing yellow sky. They are so different from each other, and yet they share the same quiet neighborhood, the same steady sun, the same ancient origins in the disk of dust and gas that circled the newborn star. They are the first of the rocky worlds, the ones formed close to the fire. And just beyond Venus, in the next orbit out, is a planet of a different character. A world where the temperatures are more moderate, where liquid water can pool on the surface, where a large moon tugs at the oceans and stabilizes the world's slow tilt. The Earth, our own quiet home, is waiting for us, and we will drift toward it now, gently, slowly, in the soft, calm dark. And so we drift now, gently and quietly, to the third planet from the Sun, our own home, Earth. We will treat it as we have treated the others, as one stop among many, a single world in a vast and mostly empty neighborhood. It is not the largest planet, not the hottest, not the coldest. It is not the most dramatic, but it has a quality that, as far as we know, is unique in all the silent reaches of the solar system. It sits in a region around the Sun where the temperature is just right for liquid water to exist on the surface, pooling in oceans, flowing in rivers, falling as rain. This region is sometimes called the habitable zone, or more simply, the Goldilocks zone. Not too hot, not too cold, but just right. It is a gentle, fortunate placement, and it has made all the difference. Earth orbits the Sun at an average distance of about 93 million miles. That distance is so stable, so reliable, that we have given it a name. We call it one astronomical unit, a quiet measuring stick for the solar system. From this distance, light from the Sun takes about 8 minutes to reach us. So when you look at the Sun, you are seeing it not as it is right now, but as it was 8 minutes ago. That warm light on your skin began its journey across the empty space nearly a quarter of an hour earlier. This is a soft, gentle kind of time travel, a reminder that even light, the fastest thing there is, takes time to cross the quiet distances of our neighborhood. The Earth itself is a rocky world, the largest of the 4 inner planets. It is about 8,000 miles across, a sphere of iron and nickel at its core, wrapped in a thick mantle of slowly churning rock, and topped with a thin, brittle crust. That crust is broken into enormous plates that float on the mantle beneath them, moving very, very slowly over millions of years. This process is called plate tectonics. The plates inch along, perhaps as fast as your fingernails grow, carrying the continents with them. They pull apart in some places, creating new ocean floor, and they push together in others, buckling the crust into mountain ranges. The Himalayas, the Andes, the Rockies, all of them are the slow, patient result of this quiet, unceasing motion. This process is still going on, right now, beneath your feet, too slow to feel, too steady to notice. It is the deep, slow breath of the planet, inhaling and exhaling over eons. And then there is the water. Earth is sometimes called the blue marble, and for good reason. About 71% of its surface is covered by liquid water, a substance that seems ordinary to us, but is rare and precious in the solar system. These vast oceans absorb heat from the Sun, store it and move it around the planet in slow, deep currents. They moderate the temperature, keeping the swings between day and night, between summer and winter, far gentler than they would be on a dry world. The oceans are also where life, as far as we understand it, first began, billions of years ago, in the warm, shallow waters of the young Earth. They are the soft, blue heart of the planet, a steady, calming presence that we can see even from far away. The atmosphere is another part of what makes Earth what it is. It is a blanket of air, mostly nitrogen and oxygen, with small amounts of other gases like argon and carbon dioxide. This blanket is just thick enough to trap the right amount of heat, keeping the average temperature at a comfortable level. It also protects the surface from the worst of the Sun's radiation and from the small meteors that constantly rain down, burning most of them up in harmless streaks of light we call shooting stars. The atmosphere is deep, but not endlessly deep. If the Earth were the size of an apple, the breathable atmosphere would be about as thick as the apple's skin. It is a thin, delicate veil, but it is enough. It is a quiet, protective presence, holding the air we breathe, the warmth we feel, and the water that cycles endlessly from ocean to cloud to rain and back again. Now, let us turn our quiet attention to the companion that has been circling the Earth for most of its history, the Moon. It hangs in our sky, a calm, silver presence, close enough to show phases and craters, far enough to pull gently on the oceans. the moon is unusually large compared to the planet it orbits. Most moons in the solar system are tiny specks next to their parent worlds. Our moon is about 1/4 the diameter of Earth, making it the largest moon relative to its planet in the whole solar system. This size, and its quiet presence, has shaped the Earth in deep and fundamental ways. The story of how the moon came to be is one of the great, slow dramas of our neighborhood's history. The leading idea, the one that fits the evidence best, is that it was born from a giant impact. About 4.5 billion years ago, when the Earth was still very young and still forming, it shared its orbit with a smaller, Mars-sized body. This object, which we call Theia, was on a path that eventually brought it into a slow, inevitable collision with the young Earth. The impact was not a glancing blow, but a massive, merging crash that destroyed Theia completely and blasted a huge amount of material from the Earth's own crust and mantle into orbit. This material, a ring of hot, glowing rock and dust, circled the wounded planet, and then, over time, through the same process of accretion that built the planets from the solar nebula, that ring of debris began to clump together. The particles stuck, and the clumps grew, and eventually, they formed a single, large body, the moon. So when you look up at the moon on a clear, quiet night, you are looking at a collection of pieces of the very early Earth, and pieces of a lost world that no longer exists. The moon is both a part of us and a quiet monument to a long-ago cataclysm that has since settled into a calm, steady orbit. The moon's gravity pulls on the Earth, and this pull creates the tides. The oceans are fluid, and they respond to the moon's gentle tug, bulging outward on the side of the Earth facing the moon, and also, in a slightly more subtle way, on the side facing away. As the Earth rotates, these bulges move across the surface, and the coastlines experience the slow, rhythmic rise and fall of the water. Twice a day, every day, the tides come in and go out, a soft, planetary breathing paced by the moon's orbit. This tidal force also has a slowing effect. The Earth's rotation is gradually, very gradually slowing down because of the friction of the tides. The day is getting longer, but so slowly that it is only noticeable over millions of years. And here is another quiet, connected fact. Because of the way gravity and motion work together, as the Earth slows its spin, the moon responds by moving slightly farther away. The moon is drifting outward, away from the Earth, by about 1.5 inches every year. That is roughly the same speed that your fingernails grow. It is an almost imperceptible separation, a slow, gentle widening of an orbit that has existed for billions of years. In the distant past, the moon would have appeared much larger in the sky. In the distant future, it will appear smaller. But for now, in our brief moment of time, it hangs at just the right distance to perfectly cover the disk of the sun during a total solar eclipse, a soft, silent alignment of size and distance that is, for us, a quiet coincidence. The moon also has a stabilizing effect on the Earth. The Earth's axis is tilted at about 23.5 degrees relative to its orbit. This tilt is what gives us our seasons, the slow annual rhythm of spring, summer, autumn, and winter. Without the moon's steadying gravitational presence, the Earth's tilt might wobble more significantly over long periods of time, leading to much more extreme climate shifts. The moon acts as a kind of gentle gyroscope, keeping the Earth's angle steady, allowing the seasons to proceed with their familiar, reliable pace. It is a quiet service, one that goes unnoticed most of the time, but it has been essential for the development of the stable, predictable environment that life has come to rely on. The moon itself is a quiet, still world. It has no atmosphere to speak of, no liquid water, no weather. The footprints left by the Apollo astronauts, pressed into the fine, gray dust of the surface, will likely remain undisturbed for millions of years. There is no wind to erase them, no rain to wash them away. The moon's surface is a frozen record, a landscape of ancient lava plains, called Maria, and heavily cratered highlands. The dark patches we see when we look up at the moon, the shapes that people sometimes imagine as a face, are those ancient lava flows, vast plains of basalt that filled in the largest impact basins. The lighter areas are the older, more heavily cratered crust, a record of the solar system's violent early days. The Moon, like Mercury, is a quiet museum, preserving the history of impacts in its silent, unchanging surface. We have looked at the Earth and its moon with the same calm, slow gaze we have used for all the other worlds. It is our home, yes, but it is also a planet, one among many, a small blue sphere drifting in the quiet dark. Its oceans, its clouds, its life, its single large companion, all of them are part of the same ancient story that shaped Mercury and Venus and the Sun itself. And just as we drifted past the first two planets, we will now continue our journey outward, moving away from this familiar blue marble, heading toward a world that is colder, redder, and quieter still. The next planet, the fourth rock from the Sun, is Mars. A desert world, a place of ancient volcanoes and vast, empty canyons, waiting for us in the calm, silent dark. We will drift toward it now, slowly, gently, in our own time. Moving outward from Earth, we cross another quiet stretch of empty space, about 40 million miles on average, though the exact distance varies as the two planets move in their orbits. Ahead of us now, growing slowly larger in the dark, is Mars, the fourth planet from the Sun, the red planet. It is the last of the rocky inner worlds, the final stop before we cross into a very different part of the solar system. Mars is smaller than Earth, about half the size, and it is colder, quieter, and far more still. It is a desert world, a place of rust-red sands, ancient volcanoes, and deep, empty canyons. It has been circling the Sun, cold and dry, for billions of years, and it holds its history written on its surface for anyone to see. The first thing we notice about Mars, the thing that gives it its familiar name, is its color. Mars is red, a deep, dusty rust red that makes it stand out even to the naked eye in the night sky. This color comes from iron oxide, essentially rust, covering much of the surface. The rocks and soil on Mars are rich in iron, and at some point in the distant past, that iron reacted with oxygen and water to form iron oxide, the same reddish-brown substance we see on an old nail left out in the rain. Over billions of years, this rusty dust has been spread across the entire planet by the thin winds, coating everything in a fine reddish powder. So when we look at Mars, we are seeing a planet that has, quite literally, rusted. It is a quiet, slow chemical process, an oxidation that has painted an entire world in shades of red and orange and brown. Mars is a cold planet. Because it is farther from the Sun than Earth, it receives less than half the sunlight we do. The average temperature on Mars is about -80 degrees Fahrenheit. On a warm summer day near the equator, the temperature might just barely climb above freezing for a few hours. But at night, even in the warmest places, it plunges far below zero. At the poles, during winter, the temperature can drop to about -225 degrees Fahrenheit, cold enough to freeze carbon dioxide out of the air as a frost, a kind of dry ice snow that blankets the polar landscapes. The atmosphere is very thin, about 1% as dense as Earth's, and it is made mostly of carbon dioxide. It is too thin to hold any significant heat, and too thin to breathe. A human standing on the surface without protection would not last long, not because of the cold alone, but because the pressure is so low that water in the body would boil away. It is a harsh environment, but a quiet one. No birds, no wind in the trees, no rushing water, just the soft, infrequent whisper of thin carbon dioxide winds stirring the fine red dust. Despite its cold and its thin air, Mars has some of the most striking landscapes in the solar system. Its surface tells a story of a world that was once much more geologically active than it is today. Let us begin with the volcanoes. Mars is home to the largest volcano known anywhere in the solar system. It is called Olympus Mons, and it is a shield volcano, meaning it was built up by countless slow, gentle eruptions of lava that spread out in broad, flat layers. Olympus Mons is enormous, so large that it almost defies easy comparison. It is about 16 miles high, which is nearly 3 times the height of Mount Everest, the tallest mountain on Earth. But it is not just tall. It is wide, incredibly wide. Its base would cover roughly the same area as the entire state of Arizona. The slopes are so gentle, so gradual, that if you were to stand on its lower flank and look up, you would not see the peak looming over you. The curve of the mountain is so broad and so low-angled that the summit would be hidden by the curvature of the planet itself. Olympus Mons is a quiet giant, a frozen monument to a time when the interior of Mars was much hotter and more active, when molten rock rose up from below and spread out in wide, calm sheets. That time has passed. The volcano is likely extinct now, silent and still, wearing its ancient lava flows like a cloak of stone. Not far from Olympus Mons lies another remarkable feature, but of a very different kind. It is a canyon system called Valles Marineris, and it is to the Grand Canyon what the ocean is to a small pond. Valles Marineris stretches for about 2,500 miles, which is roughly the distance from New York to Los Angeles. It is up to 120 miles wide in places, and it plunges to depths of up to 7 miles. That is more than 4 times deeper than the Grand Canyon. The scale of it is hard to hold in the mind. If you stood on one rim, the opposite rim would be so far away that it would be lost in the dusty haze, and the canyon floor would be so far below that the shadows would look like a deep, dark sea. Valles Marineris is not a canyon carved by a river, like the Grand Canyon. It is a rift valley, a giant crack in the crust of the planet, formed by the stretching and pulling apart of the surface as the Tharsis region, the volcanic plateau where Olympus Mons sits, bulged upward. It is a tectonic scar, a quiet, deep wound in the side of the planet, and it has been sitting there, open to the thin air, for billions of years. These giant features, the volcanoes and the canyon, speak of a Mars that was once much more active. And there is other evidence that suggests Mars was once a very different kind of world. Evidence that points to the presence of liquid water on the surface. When we look at Mars today, we see a dry, frozen desert. But scattered across the surface are features that look, from orbit, like dried-up riverbeds. There are winding channels, branching networks of valleys, and the remnants of what appear to be ancient floodplains. There are also minerals on the surface that, on Earth, only form in the presence of liquid water. Clays, hydrated sulfates, and other compounds that trap water in their crystal structure have been found in multiple locations. And at the poles, there are ice caps, layered deposits of water ice and dry ice that grow and shrink with the Martian seasons. Radar soundings from orbiting spacecraft have also detected what appears to be a large body of liquid water, very salty and very deep, buried beneath the southern polar ice cap. The evidence, taken together, quietly and calmly tells us that Mars was once a wetter world, a world with rivers, lakes, and perhaps even a shallow northern ocean. Billions of years ago, the atmosphere was likely thicker, the temperature warmer, and the surface hosted liquid water that flowed and pooled and carved the landscape. Then, over time, something changed. The atmosphere was stripped away by the solar wind, the planet cooled, the water froze or evaporated or retreated underground, and Mars became the quiet, cold desert we see today. This history of water leads to a quiet, open question, one that we do not have a firm answer for. Whether Mars ever supported any form of life remains unknown. We have not found any clear evidence of past or present life on Mars. We have found the conditions that might have made it possible, at least in the distant past. We have found organic molecules, the building blocks of life, in ancient rocks. We have found evidence of past water and past energy sources, but we have not found life itself. It is possible that microbial life once existed in those ancient rivers and lakes. It is possible that it still exists today, deep underground, where the rock is warmer and liquid water might still be present. But we do not know, and it is important to say that plainly. The question remains open. Mars keeps its secrets, buried under the red dust, waiting for a time when we might be able to look more closely. For now, the not knowing is part of the calm. Mars is simply a quiet red planet, a world of frozen deserts and ancient scars, drifting silently around the sun. Mars is not entirely alone in its orbit. It has two small moons, Phobos and Deimos. They are very different from Earth's large, round moon. Phobos and Deimos are small, irregularly shaped, and dark. Phobos, the larger of the two, is only about 14 miles across at its widest point. Deimos is even smaller, about 8 miles across. They look less like proper moons and more like lumpy, misshapen potatoes. They are both heavily cratered, their surfaces pocked and scarred by ancient impacts. Their composition suggests they are made of carbon-rich rock, similar to the asteroids found in the outer part of the asteroid belt. This has led to the prevailing idea that Phobos and Deimos are not moons that formed alongside Mars, like our moon is thought to have formed from a giant impact around Earth. Instead, they are likely captured asteroids, wanderers from the belt that strayed too close to Mars and were pulled into orbit by its gravity. They have been circling the planet ever since, two tiny, quiet companions. Phobos orbits Mars very closely, closer than any other known moon to its parent planet. It circles Mars at a distance of only about 3,700 miles from the surface. Because it is so close, it orbits very quickly, completing a full loop in just about 7.5 hours. This means that Phobos rises and sets more than 3 times in a single Martian day. And it does so in the opposite direction. Phobos rises in the west and sets in the east, moving so fast across the sky that its motion could be seen with the naked eye over the course of a few hours. Deimos, on the other hand, orbits much farther out and more slowly, taking about 30 hours to complete one orbit. It rises in the east and sets in the west, like our own moon, but it is so small that from the surface of Mars it would look like a bright star, not a disk. These two tiny, irregular moons are quiet sentinels, fragments of a distant past, captured and held by the red planet's gentle gravity. Phobos has a future that is, by cosmic standards, not very long. Its close orbit is slowly, very slowly decaying. The gravity of Mars is pulling it inward, bit by bit. In about 50 million years or so, Phobos will either break apart from the tidal stress and form a ring of debris around Mars, or it will crash into the surface. Either way, it is a quiet, slow process, a gentle end for a small moon that has circled the red planet for eons. Deimos, being farther out, will likely continue its quiet orbit for much longer, gradually drifting farther away, like our own moon is doing. These moons, small and strange, are part of the quiet tapestry of the Martian system, a final, soft detail before we leave this world behind. So Mars, the red planet, the last of the rocky inner worlds, sits in its orbit, cold and still. Its rusted surface, its giant volcanoes and deep canyons, its evidence of ancient water, its 2 tiny captured moons, all of it tells a story of a world that was once more like Earth, but that has since settled into a long, quiet old age. It is a desert, but a peaceful one, a frozen world, but one with a deep and complex history. We will leave it now, drifting slowly outward, past the orbit of Mars and into the space beyond. Ahead of us lies a region of scattered, rocky debris, a belt of leftover building blocks that never formed a planet. The asteroid belt, a quiet transitional zone, a boundary between the small, rocky inner worlds and the enormous gas giants that wait beyond. We will enter that region now, slowly, gently, letting the red planet fade behind us as we drift into the calm, sparse space between worlds. Leaving Mars behind, we drift now into a region that feels different from the orderly orbits of the planets we have visited so far. We are crossing into the asteroid belt. It is a wide, quiet zone of space that lies between the orbits of Mars and Jupiter, a kind of boundary line between the small, rocky inner worlds and the enormous gas giants that wait beyond. The asteroid belt is not a planet, and it never became one. It is instead a scattered collection of leftover material, rocky fragments and chunks of metal, the pieces that never managed to come together into a single world. It is a place of quiet, patient drifting, a reminder of the solar system's early, formative days. If you have ever seen a picture or a movie that shows a spaceship dodging and weaving through a dense field of tumbling rocks, with asteroids crashing into each other on all sides, it might be helpful to let that image go, to let it gently dissolve, and be replaced by something much calmer and much more spacious. The reality of the asteroid belt is far quieter. It is mostly empty space. The asteroids are not crowded together. They are scattered across an enormous volume, a vast ring around the Sun that is about 140 million miles wide. The average distance between any two asteroids of significant size is millions of miles. If you were to stand on one asteroid, you would not see a field of nearby rocks. You would see a dark, empty sky, with perhaps a few faint points of light that are other asteroids, so far away they look like dim stars. You could travel through the asteroid belt for your entire life and likely never come close to another object. The quiet emptiness we have felt throughout our journey is just as present here, perhaps even more so. The asteroids are lonely wanderers, each one following its own slow, silent path around the Sun. So what exactly is the asteroid belt, and why is it there? It is made up of the leftover building blocks from the formation of the solar system. You may remember the story of the solar nebula, the great spinning disk of gas and dust that gave birth to the Sun and the planets. In the inner part of that disk, the rocky material came together to form the 4 inner planets. In the outer part, the ices and gases gathered into the giant planets. But here, in the space between Mars and Jupiter, the material never finished the job. The planetesimals, the small rocky chunks that were the seeds of planets, kept colliding and breaking apart, or simply drifting, never managing to build up into a single, large body. The reason for this is thought to be the powerful gravitational influence of Jupiter. Jupiter is the largest planet, with a mass more than twice that of all the other planets combined. Its gravity is strong enough to stir up the asteroid belt, to tug on the planetesimals and disrupt their orbits, preventing them from gently coming together through accretion. The material in the belt is caught in a kind of gravitational tug-of-war between the Sun and Jupiter, and the result is that it remains scattered, a field of individual rocks instead of a single world. The asteroid belt is, in a sense, a failed planet, or perhaps more gently, a planet that never was. The total amount of material in the asteroid belt is surprisingly small. If you were to gather up every single asteroid, every rock, every grain of dust in the entire belt, and squeeze them together into a single sphere, that sphere would be smaller than our own moon. In fact, it would be only about 4% of the moon's mass. About a third of that total mass is contained in a single object, the largest resident of the belt. This object is called Ceres. Ceres is large enough and round enough that it is classified as a dwarf planet. It is about 580 miles across, roughly the size of Texas, and it is a fascinating little world in its own right. Unlike most of the other asteroids, which are irregular chunks of rock and metal, Ceres has enough gravity to have pulled itself into a roughly spherical shape. It is thought to be made of a mixture of rock and ice, and there is evidence that it may have a thin atmosphere of water vapor that comes and goes, and possibly even a subsurface layer of liquid, salty water. Ceres is a quiet, small world, a dwarf planet sitting in the middle of the belt, holding a significant fraction of the belt's entire mass in its round, icy body. Beyond Ceres, there are a few other large asteroids, though large is a relative term. Vesta is about 325 miles across. Pallas is about 318 miles across. Hygeia is about 265 miles across. These are the largest of the remaining fragments. Together with Ceres, they make up a significant portion of the belt's total mass. And then there are millions of smaller objects. Some are the size of mountains, some are the size of houses, some are the size of pebbles, and countless more are just grains of dust, tiny microscopic specks floating in the dark. The size distribution follows a pattern. There are relatively few very large asteroids, more medium-sized ones, and a vast number of very small ones. It is a quiet, orderly scattering, a cosmic size sorting that has been in place for billions of years. The asteroids themselves come in different types, different flavors of rock and metal, and these differences tell us about the early solar system. Some asteroids are made mostly of rock, similar to the rocks we find on Earth. These are the most common type in the inner part of the belt. Others are made of a mixture of rock and metal, rich in iron and nickel. These are thought to be the remnants of larger bodies that were once big enough to have their interiors melt and differentiate, with the heavy metals sinking to the core and the lighter rocks floating to the surface. When these larger bodies were later shattered by collisions, the fragments became the metallic and stony iron asteroids we see today. Still others are darker and richer in carbon, more primitive, meaning they have changed very little since the formation of the solar system. These carbon-rich asteroids are more common in the outer part of the belt. Each asteroid is a quiet, frozen piece of history, a sample of the raw materials that built the planets, preserved in the cold vacuum of space for more than 4 billion years. The asteroids are not completely still. They move. They orbit the Sun in their own individual paths, following the same gravitational rules as the planets. Most of these orbits lie in a relatively flat plane, the same plane as the planets, the remnant of the original disk of the solar nebula. But not all of them. Some have orbits that are tilted, angled relative to the rest. Some have orbits that are more elliptical, more stretched out, bringing them closer to the Sun and then farther out again. And occasionally, the gravitational tug of Jupiter, or a rare collision between two asteroids, can nudge one of these rocks out of its stable orbit and send it on a new path, a path that might cross the orbits of the inner planets. These are the asteroids that occasionally make the news, the ones whose paths come close to Earth. They are called near-Earth objects. Most of them will never hit us. The solar system is so vast, and the Earth is such a small target, that the odds of a collision are very, very low. But it does happen, very rarely, on geological timescales. The craters we see on the Moon, on Mercury, on Mars, and even here on Earth are a quiet record of these occasional encounters. They are part of the natural, slow rhythm of the solar system. Despite the occasional stray rock, the asteroid belt is, for the most part, a place of profound peace. The asteroids have been circling the Sun for billions of years, each one in its own silent, solitary orbit. They do not crash into each other often. The spaces between them are too vast. They just drift, slowly, patiently, tracing their elliptical paths through the dark. They are the leftovers, the pieces that never found a home, and they mark a boundary. Once we pass through the asteroid belt, we leave behind the realm of the small, rocky terrestrial planets. Ahead of us lies a very different kind of world, a world of gas and liquid, of swirling storms and deep, thick atmospheres. A world so large it could swallow all the other planets whole. Jupiter, the giant of our solar system, is waiting for us in the quiet dark. Its gravity is what kept the asteroid belt from becoming a planet, and that same gravity will now dominate the next stage of our journey. But for a little while longer, let us stay here in the belt, drifting among the quiet, scattered rocks. Feel the patience of this place. Nothing here is in a hurry. The asteroids have been here since the beginning, and they will likely be here until the Sun itself changes and fades. They ask nothing of us. They are just rocks, floating in the dark, holding the history of the solar system in their silent, ancient surfaces. And now, as we move slowly past them, we can see the next destination beginning to grow in the distance. A bright, pale, steady point of light, brighter than the surrounding stars. Jupiter. It is calling us forward, gently, quietly, and we will answer that call, drifting slowly out of the asteroid belt and into the realm of the gas giants. We have crossed the quiet, scattered space of the asteroid belt, leaving behind the small, rocky worlds of the inner solar system. Ahead of us now, growing slowly larger and brighter, is a planet of an entirely different kind. A world so immense that it makes everything we have visited so far seem tiny by comparison. This is Jupiter, the fifth planet from the Sun, the first of the gas giants. It is the largest planet in the entire solar system, a slow, heavy presence that has shaped the orbits and destinies of everything around it. It has no solid surface to stand on. It is a world of clouds and storms, of deepening layers of gas and liquid metal, a place of immense, quiet power. Let us begin with its size, because the size of Jupiter is the key to understanding everything else about it. Jupiter is enormous. Its diameter at the equator is about 89,000 miles. That is more than 11 times the diameter of Earth. If Jupiter were a hollow ball, you could fit more than 1,300 Earths inside it and still have room to spare. But size alone does not capture the weight, the mass of this planet. Jupiter has a mass more than twice that of all the other planets in the solar system combined. Think of that. Gather up Saturn, Uranus, Neptune, Earth, Venus, Mars, Mercury, every moon, every asteroid, every comet, every speck of dust, and put them all on one side of a giant cosmic scale. Put Jupiter alone on the other side. Jupiter would still outweigh them by more than 2 to 1. It is the heavyweight of our neighborhood, the gravitational anchor of the outer solar system. Its pull is so strong that it is thought to be the main reason the asteroid belt never became a planet, and its gravity continues to shape the orbits of comets and asteroids to this day. Despite its immense size, Jupiter is very different from the rocky planets we have visited. It is not made of rock and metal, at least not in its outer layers. Jupiter is a gas giant, which means it is made mostly of the same light, simple elements as the Sun. Hydrogen and helium. About 90% of its atoms are hydrogen, and most of the remaining 10% are helium, with just a trace of heavier elements like water, ammonia, and methane. There is no solid surface to land on, no ground beneath your feet. If you were to descend into Jupiter's atmosphere, you would just sink deeper and deeper, the gas around you growing thicker and denser, the pressure building and building, until the gas slowly, gradually, transitioned into a liquid state. And deeper still, that liquid hydrogen would become so compressed, so squeezed by the weight of everything above it, that it would take on a strange new form. It would become metallic hydrogen, a substance that conducts electricity like a metal, wrapping around a small, dense core of rock and ice. That core, if it exists, is buried under tens of thousands of miles of gas and liquid, at a pressure millions of times greater than the surface of Earth. Jupiter is a world of layers, of slow, deepening transitions, with no hard boundary between air and ground. It is a planet that simply gets thicker and heavier the deeper you go. The visible surface of Jupiter, the part we can see from space, is not a surface at all. It is the top of a deep, turbulent atmosphere, a layer of clouds that stretches down for thousands of miles. These clouds are organized into a pattern of alternating light and dark bands that wrap around the entire planet. The light bands are called zones, and they are regions where gas is rising, cooling, and condensing into high, bright clouds of ammonia ice. The dark bands are called belts, and they are regions where gas is sinking, warming, and thinning, revealing the deeper, darker layers below. This pattern of rising and sinking gas is driven by Jupiter's internal heat and its rapid rotation. Jupiter spins very fast. A single rotation, a single day on Jupiter, takes less than 10 hours. This rapid spin stretches the clouds into long, parallel bands, giving Jupiter its familiar striped appearance. The bands circle the entire planet, east-west wind patterns that can persist for decades, for centuries, or perhaps even longer. They are part of the planet's deep, steady, rhythmic circulation. Within these bands of clouds, we find one of Jupiter's most famous and long-lasting features, the Great Red Spot. It is a giant storm, an anticyclone, a high-pressure system that has been swirling in Jupiter's southern hemisphere for a very long time. The Great Red Spot is enormous. It is wider than the entire Earth. Current measurements put it at about 10,000 miles across, though it has been slowly shrinking over the past century. In the late 1800s, it was estimated to be about 25,000 miles across, wide enough to fit 3 Earths side by side. The storm rises higher than the surrounding clouds, and its reddish color, which varies in intensity over time, is thought to come from complex chemical reactions driven by ultraviolet sunlight, but the exact chemistry is not fully understood. The Great Red Spot is not a raging, chaotic hurricane in the way we might imagine an Earth storm. It is a slow, steady, rotating system. The winds around its edge howl at speeds of up to 400 miles per hour, but at its center, there is a calm, quiet eye. It is a patient, ancient storm, a quiet giant among the clouds, and it has been observed continuously for at least a few hundred years, since astronomers first trained their telescopes on Jupiter in the 1600s. We do not know exactly how long it has existed. It may have been there for much longer, a quiet, swirling presence in the southern band. And we do not know how long it will last. It may persist for centuries more, or it may slowly, gently fade away over the coming decades. Jupiter holds its secrets quietly. The energy that drives all this weather, the bands, the storms, the swirling clouds, does not come from the sun alone. In fact, Jupiter radiates more heat into space than it receives from the sun. It has its own internal heat, left over from its formation. When Jupiter formed, the immense gravitational compression of all that gas falling together generated a huge amount of heat, and the planet has been slowly, very slowly, radiating that heat into space for billions of years. This internal warmth churns the atmosphere from below, driving convection and creating the complex weather patterns we see. Jupiter is a planet that is still slowly, quietly settling, cooling from its ancient birth. Now let us turn our attention to the family of worlds that circle Jupiter. Jupiter has a large and complex system of moons. At last count, there were more than 90 confirmed moons orbiting the planet, and more small ones are being found all the time. Most of these are tiny, irregular, captured asteroids, just a few miles across. But 4 of Jupiter's moons are very different. They are large, round, and complex worlds in their own right. They are called the Galilean moons, after Galileo Galilei, the astronomer who first observed them through a telescope in the year 1610. Their names are Io, Europa, Ganymede, and Callisto. Each one is unique, a quiet, distinct world circling the giant planet. Io is the closest of the 4 to Jupiter, and it is the most geologically active body in the solar system. It is a world of volcanoes. Io is constantly being squeezed and stretched by the powerful gravity of Jupiter and the other large moons. This tidal flexing generates immense heat inside Io, keeping its interior molten and driving continuous volcanic eruptions. The surface of Io is covered in sulfur and sulfur dioxide frost, painted in shades of yellow, orange, red, and white. Volcanoes erupt plumes of gas and dust hundreds of miles into space, constantly resurfacing the moon and erasing any craters. It is a dynamic, active world, but from a distance, it is just a small, quiet point of light, silently circling its giant parent. Europa is the next moon out, and it is a world of ice. Its surface is a smooth, bright shell of frozen water, crisscrossed by long, dark cracks and ridges. Europa's surface is one of the youngest in the solar system, geologically speaking, with very few craters. The leading idea, supported by multiple lines of evidence, is that beneath this icy crust, there is a global ocean of liquid water, kept warm by the same tidal heating that powers Io's volcanoes. This subsurface ocean may be in contact with a rocky seafloor, and that contact could provide the chemical energy needed for life. Whether life actually exists there, deep in the dark, salty ocean under the ice, is an open question. Europa holds that possibility gently, quietly, beneath its frozen shell. It is a world of silent, hidden depths. Ganymede is the third of the Galilean moons, and it is the largest moon in the entire solar system. It is even larger than the planet Mercury. Ganymede is the only known moon to have its own internally generated magnetic field, a sign that it, too, may have a liquid layer deep inside, though likely a layer of salty water mixed with ice rather than a molten metal core. Its surface is a mix of dark, heavily cratered terrain and lighter, grooved regions that show evidence of past tectonic activity. Ganymede is a quiet, complex world, a moon that is almost a planet in its own right. Callisto is the outermost of the four, and it is the most heavily cratered object in the solar system. Its surface is ancient, unchanged for billions of years, a dark, icy crust pocked with countless impact craters. Callisto shows less evidence of internal activity than its siblings, and it may not be fully differentiated into distinct layers. It is a quiet, frozen record of the early solar system, a moon that has simply been sitting there, circling Jupiter, for nearly the entire history of our neighborhood. These four moons, Io, Europa, Ganymede, and Callisto, are worlds in their own right, each with its own character, its own history, its own quiet story. They circle Jupiter in a regular, rhythmic pattern, a miniature solar system inside the larger one, and they are just the largest and most famous of the family. There are dozens more, smaller and quieter, each one a captured fragment of rock or ice, a distant remnant of the solar system's formation. Jupiter's influence extends far beyond its moons. Its gravity shapes the space around it, affecting the paths of asteroids and comets. It has been called the vacuum cleaner of the solar system, because its strong gravity pulls in or deflects many of the objects that might otherwise wander into the inner solar system. In this way, Jupiter acts as a kind of quiet protector, a gravitational shield that has, over billions of years, reduced the number of impacts on the inner rocky planets. It is a gentle, steady presence, a guardian whose work is done silently and without notice. From a distance, Jupiter is a beautiful, calm planet. Its bands of clouds wrap it in soft stripes of cream, brown, orange, and white. The great red spot sits in its southern hemisphere like a quiet, watchful eye. The moons appear as tiny, bright specks, slowly moving around it in their orbits. It is a world of immense scale and immense stillness, a planet that has been slowly, quietly circling the sun for 4.5 billion years. It is the giant, the anchor, the king of our solar system, and as we drift past it, we can feel its gravity, even from a distance, a gentle reminder of its presence. But our journey is not finished. We are moving outward still, away from Jupiter, away from its bands and its storms and its family of moons. Ahead of us lies another gas giant, a planet that is almost as famous, perhaps even more famous, for its own unique feature. A planet with a system of rings so vast and so beautiful that they can be seen with a small telescope from Earth. Saturn, the ringed planet. It is waiting for us in the quiet dark, and we will drift toward it now, slowly, gently, in our own time. Moving outward from Jupiter, we cross another vast, quiet stretch of empty space. The distance between Jupiter and the next planet is enormous, about 400 million miles on average, though it varies as both worlds move in their orbits. Ahead of us, slowly growing from a bright point of light into a pale, golden disk, is a planet that many people think of as the most beautiful in the solar system. Saturn, the sixth planet from the Sun, the ringed world. It is the second of the gas giants, and while it shares many qualities with Jupiter, it has a character all its own, a quieter, more delicate presence that invites a long, slow gaze. Saturn is a gas giant, like Jupiter. It is made mostly of hydrogen and helium, with no solid surface to stand on. It is the second largest planet in the solar system, with a diameter of about 75,000 miles, roughly 9.5 times the width of Earth. But Saturn is less massive than Jupiter. In fact, Saturn has only about 1/3 of Jupiter's mass, despite being nearly as large in terms of volume. This brings us to a quiet, almost playful fact about Saturn. It is the least dense of all the planets. Its average density is less than the density of water. If you could find a body of water large enough to hold it, Saturn would float. It would bob on the surface like a giant, pale beach ball. This is because Saturn is made almost entirely of the lightest elements, hydrogen and helium, and it has not been compressed by its own gravity to the same extreme degree as Jupiter. The planet is, in a sense, a giant, fluffy ball of gas, held together by its own gentle gravity, floating serenely in the dark. Like Jupiter, Saturn has no solid surface. Its visible face is the top of a deep, thick atmosphere, banded with stripes of pale yellow, gold, and cream. These bands are similar to Jupiter's zones and belts, regions of rising and sinking gas, but they are much more subtle, much softer. The colors are muted, gentle, like watercolor washes on a pale canvas. The atmosphere is also home to storms, though they are less prominent than Jupiter's great red spot. Occasionally, a large storm will form and spread across a band, a pale, turbulent region that eventually fades back into the quiet stripes. Saturn, like Jupiter, radiates more heat than it receives from the Sun, slowly releasing the ancient warmth of its formation into space. It is a world of quiet, deep internal warmth, a soft glow that drives the slow churning of its atmosphere. But it is not the planet itself that makes Saturn so remarkable, so memorable. It is the rings. The rings of Saturn are one of the most beautiful and iconic sights in the entire solar system. They are a vast, flat disk of countless individual pieces of ice and rock, circling the planet in a thin, delicate plane. From a distance, they look solid, like a series of smooth, concentric circles painted around the planet. But up close, we can see that they are made of individual fragments, ranging in size from tiny grains of dust to chunks as large as houses. The vast majority of the ring material is water ice, plain frozen water, with a small amount of rocky dust mixed in. This ice is what gives the rings their bright, reflective appearance. They shine in the sunlight, a pale, shimmering halo around the golden planet. The rings are enormous in width. The main ring system stretches from about 4,000 miles above Saturn's cloud tops out to about 50,000 miles above the clouds. That is a span of nearly 170,000 miles from one outer edge to the other. They are so wide that if you placed Earth at the center of Saturn, the rings would stretch far past the orbit of the Moon. And yet, despite this vast width, the rings are incredibly thin. In most places, they are no more than a few hundred feet thick. In some places, they are less than a mile thick. If you could shrink the rings down to the size of a sheet of paper, that sheet of paper would be so thin that it would be nearly transparent. The rings are a vast, delicate, two-dimensional structure, a whisper of ice and dust floating around the planet. The rings are not a single, solid disk. They are divided into multiple sections, separated by gaps. The largest and most famous gap is called the Cassini division, a dark, empty band that separates the bright, broad A ring from the even brighter B ring. There are other, fainter rings inside and outside these main ones, each with its own character, its own density, its own quiet personality. The gaps are caused by the gravitational influence of Saturn's moons. The small moons orbit within or near the rings, and their gravity clears out the spaces, sweeping the particles away and creating the dark, empty bands. These moons are sometimes called shepherd moons, because they shepherd the ring particles, keeping them in place, maintaining the structure of the rings with their quiet, steady gravity. There is a gentle, open question about the rings, one that adds to their quiet mystery. How old are they, and how long will they last? For a long time, it was thought that the rings formed alongside Saturn, billions of years ago, from the same primordial material that formed the planet. But more recent evidence suggests that the rings may be much younger. They are bright and clean, made mostly of pure ice, and they are losing material at a steady rate. Micrometeorites constantly bombard the rings, darkening and eroding the particles, and the ring material itself is slowly, very slowly, raining down onto Saturn's atmosphere, a process called ring rain. Based on these observations, some scientists now think that the rings may be only a few 100 million years old, and that they may not last forever. They could be a temporary, fleeting feature, a brief, beautiful moment in the long, slow life of the solar system. It is possible that a large comet or icy moon strayed too close to Saturn and was torn apart by its gravity, and the debris spread out into the rings we see today. We do not know for certain. The origin and age of Saturn's rings remain a topic of quiet study, a gentle, open question. The not knowing is part of their beauty. They simply are, right now, a pale, shimmering halo, and we can appreciate them without needing to know every detail of their past. Saturn, like Jupiter, has a large family of moons. At last count, there were more than 140 known moons orbiting Saturn, more than any other planet in the solar system. Most of these are small, irregular, captured bodies, just a few miles across. But some of Saturn's moons are large, complex, and fascinating worlds in their own right. We will gently drift past two of the most notable ones. The first is Titan. Titan is Saturn's largest moon, and it is a world of its own, larger than the planet Mercury. It is the only moon in the solar system with a thick, dense atmosphere. That atmosphere is made mostly of nitrogen, like Earth's, but with a significant amount of methane and other hydrocarbons. The atmospheric pressure at the surface of Titan is about 1.5 times the pressure at sea level on Earth. If you were to stand on Titan, you would not need a pressurized suit, though you would need protection from the cold and the lack of oxygen. The temperature on Titan is about -290 degrees Fahrenheit, cold enough that methane can exist as a liquid, and indeed, Titan has lakes and rivers and seas of liquid methane and ethane. It is the only other body in the solar system known to have stable bodies of liquid on its surface. There are river channels, drainage networks, and large, dark lakes near the poles. It is a world with weather, with a methane cycle that mirrors the water cycle on Earth, with evaporation, clouds, and rain. It is a cold, alien, but deeply familiar landscape, a quiet, slow-motion version of the processes we know on our own world. The second moon is Enceladus. Enceladus is much smaller than Titan, only about 300 miles across. It is a bright, icy moon, covered in a smooth, reflective surface of frozen water. But Enceladus is not a dead, frozen world. Observations from the Cassini spacecraft, which orbited Saturn for 13 years, revealed that Enceladus is actively spewing plumes of water vapor, ice particles, and organic molecules from cracks in its south polar region. These plumes shoot out into space, forming a faint, icy ring around Saturn called the E-ring. The heat that drives this activity comes from tidal flexing, the same kind of gravitational squeezing that powers Io's volcanoes around Jupiter. This suggests that there is a global ocean of liquid water beneath the icy crust of Enceladus, kept warm by the tidal forces. The plumes contain not just water, but salts, silica particles, and complex organic molecules, all the ingredients that, on Earth, are associated with hydrothermal systems that can support microbial life. Whether Enceladus actually hosts any form of life is an open question. It is a quiet, gentle possibility, a hidden ocean beneath the ice, silently cycling through its own slow rhythms. These moons, Titan and Enceladus, along with the many others, make Saturn's system a rich and varied place. The planet itself, with its soft, golden bands and its delicate, shimmering rings, is a picture of quiet beauty. It has been circling the sun for more than 4 billion years, its rings slowly evolving, its moons drifting in their orbits. It is a world that invites stillness, a slow, calm gaze. There is no rush here. The rings spin at their own pace, the moons trace their paths, the clouds drift in the pale, golden atmosphere. Saturn is a place of deep, quiet peace. And so, as we drift past Saturn, letting its image linger softly in our minds, we continue our slow journey outward. The sun is growing dimmer now, smaller in the distance. The next two planets are farther away, colder and stranger. They are a different class of world entirely. They are called ice giants, and the first of them is waiting for us in the quiet dark. Uranus, a planet tilted on its side, spinning slowly, its pale blue-green color a whisper of the deep cold that fills this outer region of the solar system. We will drift toward it now, slowly, gently, as Saturn's rings fade softly behind us into the dark. We have left the realm of the gas giants, Jupiter and Saturn, with their deep hydrogen atmospheres and their swirling storms. Ahead of us now, moving deeper into the cold, dim outer reaches of the solar system, is a different kind of world. A planet that is smaller than the gas giants, colder, and composed of different materials. This is Uranus, the seventh planet from the Sun, the first of the ice giants. It is a world of pale blue-green light, a quiet, tilted, distant sphere that has been circling the Sun in its own strange, slow way for billions of years. Uranus is far away. It orbits the Sun at an average distance of about 1.8 billion miles. That is about 19 times farther from the Sun than Earth is. At this distance, the Sun is no longer the blazing disk we know. It appears as a small, bright point of light, still far brighter than any star, but a point nonetheless. The sunlight that reaches Uranus is only a tiny fraction of what we receive on Earth, less than 1/300th. The temperature in the upper atmosphere of Uranus is about -350 degrees Fahrenheit, making it the coldest planetary atmosphere in the solar system, even colder than Neptune, which is farther away. Uranus is a world of deep, quiet cold, a place where the sun is more of a memory than a presence. Uranus is called an ice giant, and this name tells us something important about what it is made of. The gas giants, Jupiter and Saturn, are mostly hydrogen and helium, the lightest and most abundant elements in the universe. Uranus, by contrast, is made largely of heavier materials, what scientists call ices. These are not necessarily frozen solid like an ice cube, but rather a hot, dense fluid of water, ammonia, and methane, mixed in with rock and wrapped around a small, rocky core. This icy, slushy mantle makes up most of the planet's mass. Surrounding this mantle is an outer atmosphere of hydrogen and helium, but it is a much thinner layer than the vast atmospheres of Jupiter and Saturn. Uranus is, in essence, a world built mostly of ices and rock, a different recipe from its larger siblings. It is a quieter, colder, denser kind of giant. The most striking thing about Uranus, the feature that sets it apart from every other planet in the solar system, is its tilt. Uranus spins on its side. The axis of rotation, the imaginary line around which the planet spins, is tilted at about 98 degrees relative to its orbit around the Sun. This means that Uranus essentially rolls around the Sun like a ball, rather than spinning like a top the way the other planets do. While Earth's axis is tilted at about 23.5 degrees, giving us our familiar seasons, Uranus is tilted so far that its poles point almost directly at the Sun at certain points in its orbit. This extreme tilt is one of the great quiet mysteries of the outer solar system. We do not know exactly what caused it. The leading idea is that, early in its history, Uranus was struck by a large object, perhaps another protoplanet, a collision so powerful that it knocked the entire planet over onto its side. The debris from that collision may have formed the planet's moons and rings, but the exact details are not settled. The tilt remains a quiet, open question, a gentle reminder that the solar system's history was not always as calm as it is now. This extreme tilt gives Uranus seasons that are unlike anything we experience on the other planets. Uranus takes about 84 Earth years to complete one orbit around the Sun. Because of its sideways spin, each pole gets about 42 years of continuous sunlight, followed by 42 years of continuous darkness. At the height of summer at the North Pole, The sun is almost directly overhead, and it does not set for decades. The atmosphere warms, slightly, and weather patterns shift. Then, as the planet moves along its orbit, the sun slowly sinks toward the horizon, and eventually, for the next 42 years, the North Pole is plunged into a long, dark winter. Meanwhile, the South Pole is enjoying its own decades-long summer. These are not seasons in the way we think of them. They are slow, vast, planetary rhythms, a deep, measured breathing of light and dark that takes almost a human lifetime to complete. Right now, from our perspective on Earth, we are seeing Uranus with its North Pole facing us, so the planet appears as a pale, featureless disk, its bands and storms hidden from view. The color of Uranus is a soft, pale blue-green, a color that is quiet and calming to look at. This color comes from methane in its upper atmosphere. Methane gas absorbs red light from the sun and reflects blue and green light back into space. It is the same process that gives Neptune its deeper blue color, but on Uranus, the effect is more muted, more pastel. The planet appears as a smooth, almost featureless sphere, with only faint bands and occasional clouds visible. Uranus lacks the dramatic storms and prominent bands of Jupiter and Saturn. Its atmosphere is calmer, quieter, less turbulent. It is a world of deep, slow internal processes, a planet that seems to be at peace, drifting silently through the cold. Uranus has a system of rings, but they are nothing like the bright, broad rings of Saturn. The rings of Uranus are dark, narrow, and faint. They were discovered by accident in 1977, when astronomers watched Uranus pass in front of a distant star and noticed the star's light flickering on and off before and after the main event. The rings are made of dark material, probably radiation-processed organic compounds and ice, and they are very thin and very narrow. There are 13 known rings in total, each one a delicate, dark thread circling the planet. They are quiet, subtle features, visible only with powerful telescopes and special techniques. But they are there, a faint echo of the more famous rings around Saturn. Uranus also has a family of moons. There are 27 known moons orbiting Uranus, and they are all named after characters from the works of William Shakespeare and Alexander Pope, a quiet literary touch that adds to the gentle, contemplative feel of this distant world. The largest moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Titania is the largest, about 980 miles across, roughly half the diameter of our own moon. These moons are made of a mix of ice and rock, and their surfaces are heavily cratered, scarred by ancient impacts. Miranda, the smallest of the 5 major moons, is a strange and fascinating world. Its surface is a jumbled patchwork of different terrains, with deep canyons, cliffs, and smooth plains, as if the moon was shattered and then reassembled in a haphazard way. This may be a record of a giant impact in its past, a collision that broke Miranda apart and then allowed gravity to pull the pieces back together. Whatever the cause, Miranda is a quiet, frozen puzzle, a small moon with a complex and mysterious history. As we drift past Uranus, we are now very far from the sun indeed. The light is dim, the cold is deep, the distances between worlds are growing vaster. Uranus was the first planet to be discovered with a telescope by the astronomer William Herschel in 1781. Before that, it was unknown, unseen, just a faint point of light lost among the stars. It had been there all along, of course, quietly circling the sun for billions of years, unnoticed by human eyes. That is a gentle thought to hold as we move through the outer solar system. There is so much out here, so much that is quiet and distant and unknown. And even now, our understanding is incomplete. We have only sent one spacecraft to visit Uranus, Voyager 2, which flew past in 1986. Everything else we know comes from telescopes on and around Earth. The ice giant keeps its secrets, its tilted axis, its faint rings, its cold, calm atmosphere. It simply is, a quiet presence at the edge of our vision. But our journey is not quite finished. There is one more officially recognized planet to visit, one more world that waits in the dim, cold dark. It is the eighth planet, the farthest from the Sun, and in some ways, it is the windiest, the most distant outpost of the major planetary family. Neptune, a deep blue world, named for the Roman god of the sea, sits out there in the quiet, its winds howling silently in the thin, cold air. We will drift toward it now, slowly, gently, leaving the pale blue-green of Uranus behind us, moving ever outward into the quiet dark. We are now very far from the Sun. The pale blue-green of Uranus has faded behind us, and we are drifting through the coldest, darkest part of the planetary realm. Ahead of us, growing slowly from a dim speck into a small, deep blue disk, is the last of the officially recognized planets. Neptune, the eighth planet from the Sun, the final outpost of the major worlds. It is an ice giant, like Uranus, but it has a character all its own, a world of deep, vivid blue, of the fastest winds ever recorded, and of a moon that dances backward in its orbit. Neptune is the quiet, distant edge of the planetary family, a world that has been circling the Sun in patient silence for 4.5 billion years. Neptune is far away, so far that the numbers can feel almost dreamlike. It orbits the Sun at an average distance of about 2.8 billion miles. That is 30 times farther from the Sun than Earth is. At this distance, the Sun appears as a tiny, brilliant point of light, far smaller than we can easily imagine. The sunlight that reaches Neptune is only about 1/900th of what we receive on Earth. It is a dim, cold realm, where the Sun is more a distant star than a warm presence. Because Neptune is so far out, it takes a very long time to complete one orbit around the Sun. A single year on Neptune lasts about 165 Earth years. Think of that. The last time Neptune was in the same position it is now, back in the 1850s, the world on Earth was a very different place. The planet has been slowly, patiently tracing its vast circle around the Sun, unhurried, unbothered, for all of human history and far beyond. Since its discovery in 1846, it has not yet completed even one full orbit. It is a world on a timescale that makes our own lives feel like brief, soft breaths. Neptune is an ice giant, the twin of Uranus in many ways, but not quite the same. It is slightly smaller in diameter than Uranus, about 30,000 miles across, but it is actually more massive. Neptune has a higher density, which suggests it contains a larger proportion of heavier materials in its interior. Like Uranus, Neptune is made largely of a hot, dense fluid of water, ammonia, and methane ices, surrounding a small, rocky core. Its outer atmosphere is mostly hydrogen and helium, with a significant amount of methane, and it is the methane that gives Neptune its most striking feature, its color. Neptune is a deep, vivid blue, much richer and more intense than the pale, soft blue-green of Uranus. The methane in Neptune's atmosphere absorbs red light from the Sun and reflects blue light back into space. But the exact reason why Neptune is so much bluer than Uranus, which has a similar amount of methane, is not fully understood. There must be some other component in the atmosphere, some subtle chemistry or layer of haze, that deepens the blue. It is a quiet, gentle mystery, a question that remains open. The planet simply is a beautiful, deep azure, a sapphire hanging in the far dark. Despite its distance from the Sun and its cold, quiet appearance, Neptune is a world of surprisingly active weather. It has the strongest sustained winds recorded on any planet in the solar system. In its upper atmosphere, winds can reach speeds of over 1,000 miles per hour. To put that in perspective, the strongest winds ever recorded on Earth, in the most powerful hurricanes, are about 200 miles per hour. Neptune's winds are 5 times faster. These winds are not like the winds we know on Earth, which are driven by the Sun's heat. Neptune receives very little solar energy. Instead, its winds are thought to be driven by the planet's own internal heat. Like Jupiter and Saturn, Neptune radiates more heat into space than it receives from the Sun. It has a warm interior, left over from its formation, and this internal warmth churns the atmosphere, driving the powerful, silent winds that howl through the deep blue clouds. The winds on Neptune are organized into bands, similar to the other giant planets, and they can create large storms. When Voyager 2 flew past Neptune in 1989, it observed a giant dark spot in the southern hemisphere, a storm system similar to Jupiter's Great Red Spot, though not as long-lasting. That storm, called the Great Dark Spot, had since faded, and new dark spots have been observed to come and go in Neptune's atmosphere. The planet is dynamic, active, but in a quiet, distant way. The storms rage silently in the thin, cold air, unseen by any eyes but our telescopes. Neptune has a system of rings, like the other giant planets, but they are very faint and dark. They are made mostly of dust and small particles, and they are difficult to see, even with the best telescopes. There are at least 6 known rings, each one a delicate, shadowy arc or circle around the planet. They are quiet, subtle features, a faint echo of the grand rings of Saturn, a reminder that ring systems are common among the giant planets, each one unique in its own way. Neptune also has a family of moons. There are 16 known moons orbiting the planet, and like the moons of Uranus, they are a quiet, scattered collection of icy and rocky bodies. Most are small, irregular, and captured, but one of them stands out: Triton. Triton is Neptune's largest moon, and it is a truly remarkable world. It is about 1,680 miles across, making it slightly smaller than our own moon. But Triton is not like most other large moons in the solar system. For one thing, it orbits Neptune backward. In the language of astronomy, it has a retrograde orbit. It moves around Neptune in the opposite direction to the planet's own spin. This is a very strong clue that Triton did not form alongside Neptune. A moon that forms from the same cloud of material as its planet will orbit in the same direction as the planet's rotation. A backward orbit means Triton must have formed somewhere else, likely in the Kuiper Belt, the region of icy debris beyond Neptune, and was later captured by Neptune's gravity. Triton is, in essence, a captured dwarf planet, a visitor from the frozen outer reaches that was pulled into orbit around the blue giant. Being captured is a violent process, gravitationally speaking, and it would have left Triton in an elliptical, tilted orbit that gradually, over time, became more circular. This process would have generated immense heat through tidal friction, and that heat shaped Triton into the world we see today. Triton is one of the coldest known objects in the solar system, with a surface temperature of about -391 degrees Fahrenheit, just a few degrees above absolute zero. Its surface is a mix of frozen nitrogen, water ice, and carbon dioxide ice, and it is geologically active. Voyager 2 observed active geysers on Triton, erupting plumes of nitrogen gas and dark dust several miles into the thin atmosphere. These geysers are powered by the faint warmth of the sun, which, even at this great distance, is enough to vaporize the nitrogen ice beneath the surface, building up pressure until it erupts. Triton has a thin atmosphere of nitrogen, and its surface shows evidence of cryovolcanism, the slow, cold flowing of icy materials. It is a frozen, active world, a captured wanderer, circling Neptune in its quiet, backward path. The discovery of Neptune itself is a gentle, thoughtful story. It was the first planet to be found not by someone looking through a telescope and noticing it, but by mathematics. Astronomers studying the orbit of Uranus noticed that the planet was not moving exactly as predicted. There was a slight wobble, a subtle deviation that suggested the gravitational pull of an unseen body. They calculated where that body should be, and when they pointed their telescopes at that spot, there it was, Neptune, a new world, found by the quiet power of reason and observation. It is a reminder that the solar system is a place of predictable, orderly laws, where gravity works the same way everywhere, and where careful, patient study can reveal things that have never been seen. As we drift past Neptune, we have now visited all 8 of the major planets. The 4 rocky inner worlds, Mercury, Venus, Earth and Mars. The asteroid belt, that quiet, scattered boundary. The two gas giants, Jupiter and Saturn, with their deep atmospheres and families of moons. And the two ice giants, Uranus and Neptune, the cold blue sentinels at the edge of the planetary realm. But our journey is not yet over. Beyond Neptune lies a vast, wide region of icy debris, a disk of leftover material from the solar system's formation. This is the Kuiper Belt, and it is home to Pluto, the most famous of the dwarf planets, and many other small, frozen worlds. We are crossing now into the solar system's outer frontier, a place of deep cold and profound quiet, a place where the sun is just a distant point of light. We will drift into that region now, slowly, gently, letting the deep blue of Neptune fade behind us as we move ever outward into the dark. We have left the orbit of Neptune behind us now, the last of the major planets fading softly into the dark. Ahead of us stretches a region that is vast, cold, and sparsely populated. This is the Kuiper Belt. It is a wide, disc-shaped zone of icy debris that begins just beyond Neptune and extends far, far outward, billions of miles across. If the asteroid belt between Mars and Jupiter is a scattering of rocky leftovers, the Kuiper Belt is its colder, larger, icier counterpart. It is the solar system's frozen outer frontier, a quiet realm of small worlds, dwarf planets, and countless smaller icy fragments, all drifting slowly in their distant orbits around the Sun. The Kuiper Belt is enormous. Its inner edge is roughly at the orbit of Neptune, about 2.8 billion miles from the Sun. Its outer edge is less well defined, but it extends out to at least 5 billion miles, and some estimates place its boundary much farther. This is a region of the solar system where the Sun's light is faint and weak, where temperatures hover just a few degrees above absolute zero, and where the objects that live there are made mostly of frozen water, methane, ammonia, and other ices. The Kuiper Belt is similar in shape to the asteroid belt, a flat disk aligned with the plane of the planets, a remnant of the original solar nebula that gave birth to everything. But it is much larger, maybe 20 times wider, and it contains perhaps 200 times as much material. It is the source of many of the short-period comets, the ones that swing through the inner solar system on predictable orbits of less than 200 years. These comets are Kuiper Belt objects that have been nudged inward by gravity, sent on long, looping journeys toward the Sun. Like the asteroid belt, the Kuiper Belt is mostly empty space. The objects out here are scattered across a volume so immense that collisions are extremely rare. The average distance between any two significant Kuiper Belt objects is millions of miles. It is a place of deep, profound quiet. The objects drift in their slow orbits, taking hundreds or even thousands of years to complete a single loop around the Sun. They are the leftover building blocks, the pieces that never manage to gather into a full-sized planet. Out here, far from the Sun, the process of planetary formation was just too slow. The material was too spread out, and the orbital speeds were too low for the gentle accretion we saw in the inner solar system to build anything larger than a dwarf planet. So the Kuiper Belt remains a frozen archive, a collection of ancient, unchanged worlds from the earliest days of the solar system. The most famous resident of the Kuiper Belt is Pluto. For most of the time since its discovery, Pluto was known as the ninth planet. It was found in 1930 by Clyde Tombaugh, a young astronomer working at the Lowell Observatory in Arizona, after a patient, careful search of the night sky. For 76 years, Pluto held its place as the smallest, most distant, and most mysterious of the planets. But as we learned more about the outer solar system, we began to find other objects out there, objects that were similar to Pluto in size and composition. Eris, discovered in 2005, is actually slightly more massive than Pluto. This led to a quiet, thoughtful conversation among astronomers about what exactly defines a planet. In 2006, the International Astronomical Union created a new category, dwarf planet. A dwarf planet is a body that orbits the Sun, has enough gravity to pull itself into a roughly round shape, but has not cleared its orbit of other debris. Pluto, along with Eris and several other Kuiper Belt objects, was reclassified under this new definition. Pluto is no longer considered the ninth planet. It is now known as a dwarf planet, one of the largest and most well-known members of the Kuiper Belt. This change was not a demotion but a reclassification, a refinement of our understanding. It is a gentle reminder that our knowledge of the universe grows and deepens over time, and that categories are tools we use to make sense of things, not fixed, permanent truths. Pluto is a small, cold, and surprisingly complex world. It is only about 1,470 miles across, smaller than our own moon. It orbits the Sun at an average distance of about 3.7 billion miles, but its orbit is not a neat circle. It is an ellipse, a stretched-out oval, that sometimes brings Pluto slightly closer to the Sun than Neptune. During these times, Pluto crosses inside Neptune's orbit, though there is no danger of collision. Their orbits are timed in a way that keeps them safely apart. Pluto takes about 248 Earth years to complete one orbit around the Sun. A single year on Pluto is longer than the entire history of the United States. From Pluto's surface, the Sun would appear as a brilliant point of light, far brighter than any star, but small enough to cover with a grain of sand held at arm's length. The daylight on Pluto is dim, like twilight on Earth just after sunset, and the temperature is about -375 degrees Fahrenheit. Pluto's surface is a patchwork of different terrains. There are mountains made of water ice, which at these temperatures is as hard as rock. There are vast, smooth plains of frozen nitrogen, carbon monoxide, and methane ices. There are glaciers, slow-moving rivers of solid nitrogen that flow, very slowly, across the surface. And there is a thin atmosphere, mostly nitrogen with traces of methane, that expands when Pluto is closer to the Sun and collapses as frost onto the surface when it moves farther away. This atmosphere is only about 100,000th as dense as Earth's, a faint, temporary veil of gas that comes and goes with the slow, deep seasons. Pluto is a geologically active world, with processes driven not by internal heat from radioactive decay, but by the slow, seasonal cycling of its surface ices. It is a dynamic, living world, despite its small size and great distance. Pluto does not travel alone. It has a large moon, Charon. Charon is about half the diameter of Pluto, which is an unusually large size ratio for a moon and its planet. In fact, Charon is so large relative to Pluto that the two bodies orbit a shared point of gravity, a barycenter, that lies in the space between them, rather than inside Pluto itself. They are a binary system, a pair of worlds dancing around each other as they slowly circle the Sun. Charon's surface is different from Pluto's, darker and more heavily cratered, with a large, reddish polar cap, thought to be made of organic compounds captured from Pluto's escaping atmosphere. The two worlds are tidally locked, always showing the same face to each other. If you stood on the surface of Pluto and looked up, you would see Charon hanging in the sky, unmoving, a constant, quiet companion. Pluto also has 4 smaller moons: Styx, Nix, Kerberos, and Hydra. They are tiny, irregularly shaped bodies, just a few miles across, orbiting farther out than Charon. They are faint, small, and quiet, a tiny family of moons circling the binary pair. The whole Pluto system is a delicate, complex little world at the edge of our knowledge, a place that was just a point of light for most of human history, and is now a rich landscape of mountains and plains and ices, revealed by the patient, quiet work of exploration. Beyond Pluto, the Kuiper Belt is home to many other dwarf planets and large objects. Eris, as mentioned, is slightly more massive than Pluto, and it has its own small moon, Insomnia. Eris orbits even farther out than Pluto, with a highly elongated orbit that takes it nearly 100 times farther from the Sun than Earth. Its surface is covered in methane ice, and it appears almost perfectly white. Haumea is another dwarf planet in the Kuiper Belt, shaped like an elongated egg, spinning very rapidly, with a ring system and 2 small moons. Makemake is another, a reddish world covered in methane ice, with a single small moon. These are all worlds that have only recently come into our awareness, faint points of light that are slowly resolving into real places as our telescopes and spacecraft get better. They are quiet, distant, and mysterious, and they remind us how much we still do not know. Much of the Kuiper Belt remains unexplored. We have only sent one spacecraft, New Horizons, to visit this region. It flew past Pluto in 2015, giving us our first close-up views of that distant world, and then continued on to visit a smaller Kuiper Belt object called Arakoth in 2019. Arakoth is a contact binary, 2 small, round lobes stuck together, a pristine, ancient building block from the solar system's earliest days. It is a quiet, frozen fragment, unchanged for billions of years. Everything else we know about the Kuiper Belt comes from telescopes, and there is so much more out there waiting to be found. New small objects are being discovered all the time, and it is plainly acknowledged that our map of this region is far from complete. We do not know how many dwarf planets there are. We do not know the full extent of the belt. We do not know what other strange and beautiful worlds might be drifting out there in the cold. And that is perfectly all right. The not knowing is part of the calm. The Kuiper Belt keeps its secrets, holding them in its frozen, distant darkness, asking nothing of us. As we drift through this quiet, icy realm, the sun is now so far away that it is just one bright star among many. The cold is deep and absolute. The distances between objects are so vast that each one is utterly alone, a solitary world tracing its slow, patient path through the dark. The Kuiper Belt is a place of profound stillness, a frontier where the solar system slowly fades into the interstellar night. And yet, even this is not the end. Far beyond the Kuiper Belt, there is thought to be an even larger, more distant structure, a vast, spherical shell of icy debris that surrounds the entire solar system, the Oort cloud. It is the final, quietest boundary, and we will drift toward it now, slowly, gently, moving ever outward into the soft, calm dark. We have drifted past the planets, past the asteroid belt, past the Kuiper Belt, and now we are entering the most distant, most quiet realm of all. A place so far from the sun that its very existence is still, in many ways, a gentle mystery. This is the Oort cloud. It is not a cloud in the way we normally think of one. It is a vast, spherical shell of icy debris, a halo of frozen fragments that surrounds the entire solar system. If the Kuiper Belt is the outer disk, the Oort cloud is the outer sphere, an enormous bubble of leftover material that marks the practical edge of the sun's gravitational influence. It is the final boundary, the place where our solar system whispers its last faint hello to the interstellar space beyond. The Oort cloud is so far away that the numbers we use to describe it start to lose their grip on the imagination. While the Kuiper Belt extends out to maybe 5 or 10 billion miles from the sun, the Oort cloud is thought to begin much farther out, perhaps 100 billion miles, and to stretch out to perhaps 10 trillion miles or more. That is so far that light from the sun takes more than a year to reach its outer edge. The nearest star to our sun, Proxima Centauri, is about 25 trillion miles away, and the Oort cloud may extend nearly halfway to that distant neighbor. It is a vast, diffuse, spherical shell of icy bodies, a quiet, frozen boundary between our solar system and the rest of the galaxy. It is important to say, calmly and plainly, that the Oort cloud has never been directly observed. No telescope has ever seen an Oort cloud object in its distant home. The objects out there are simply too small, too dark, and too far away to be detected with our current instruments. The existence of the Oort cloud is inferred, which means we have reasoned it out from other evidence. The main evidence comes from comets, specifically from a class of comets called long-period comets. These are comets that fall into the inner solar system from all directions, not just along the flat plane of the planets, and they have orbits that take them on incredibly long, stretched-out journeys that last thousands or even millions of years. Their paths suggest they come from a vast, spherical reservoir of icy bodies far beyond the Kuiper Belt. That reservoir is what we call the Oort cloud. We have not seen it, but the comets tell us it is there. It is a quiet, reasonable deduction, a shadow in the dark that we can infer from the behavior of the things that visit us from its depths. So what exactly are these objects in the Oort cloud? They are thought to be the same kind of icy planetesimals that make up the Kuiper Belt, but they are much farther out and much more spread apart. They are made of ice, dust, and rock, the primordial material that was present at the birth of the solar system. They are sometimes described as dirty snowballs, a phrase that captures their basic nature well enough. They are chunks of frozen water, frozen methane, frozen ammonia, and frozen carbon dioxide, mixed with rocky dust and organic compounds. They are the leftover ingredients that never became planets, the scattered, untouched remnants of the solar nebula. In the inner part of the solar system, these icy bodies either merged into the planets or were thrown out by the gravity of the giant planets. The ones that were thrown out to the farthest reaches, not entirely escaping but not falling back either, settled into the vast, spherical shell of the Oort cloud. They have been out there, in the deep cold, for billions of years, barely changed since the very beginning. Occasionally, very occasionally, one of these icy bodies is disturbed. A passing star, drifting by at a distance of trillions of miles, can give a gentle gravitational nudge. Or the overall tidal pull of the Milky Way galaxy itself can slowly, subtly alter an orbit. When this happens, an Oort cloud object might be sent inward, falling toward the Sun on a long, slow journey that takes thousands of years. As it falls, it crosses the vast emptiness of the outer solar system, then the Kuiper Belt, then the orbits of the giant planets, and finally it enters the inner solar system. As it gets closer to the Sun, it begins to warm. The ices on its surface start to vaporize, turning directly from solid to gas. This releases dust and gas that stream away from the nucleus, the solid core of the comet, and form a glowing halo called a coma. The solar wind and the pressure of sunlight then push this material outward, away from the Sun, creating the long, glowing tails that comets are famous for. A comet actually has two tails, one made of dust, which is pushed by sunlight and curves gently along the comet's path, and one made of ionized gas, which is pushed by the solar wind and points straight away from the Sun. These tails can stretch for millions of miles, glowing softly in the dark. When we see a comet in the night sky, we are seeing a visitor from the Oort cloud, a frozen fragment of the solar system's birth, awakened briefly by the warmth of the Sun before it swings back out into the cold for another long, long sleep. Some comets are more familiar to us because they return on shorter, predictable cycles. Halley's Comet is perhaps the most famous. It returns to the inner solar system about every 76 years, and its appearances have been recorded by humans for thousands of years. Halley's Comet is not an Oort cloud comet, though. It is thought to be a short-period comet, one that originated in the Kuiper Belt and was captured into a shorter orbit by the gravity of the planets. True Oort cloud comets have much longer orbits. Some may take thousands of years to complete one loop. Others may take millions. A comet that visits the inner solar system only once in a million years is a messenger from the very edge of our home, bringing with it a tiny sample of the primordial material that formed everything. The Oort cloud is not a dense, crowded place. Far from it, the objects out there are separated by vast, immense distances. The average spacing between individual Oort cloud bodies is thought to be tens of millions of miles, perhaps comparable to the distance between Earth and Mars. It is a region of profound isolation. Each icy fragment is alone in the dark, drifting slowly, so slowly, around the distant Sun. The temperature out there is only a few degrees above absolute zero, the point where all thermal motion of atoms nearly ceases. The sun is not a disk. It is not even the brightest star in the sky. It is just a faint point of light, lost among the other points of light. An observer on an Oort cloud object would have no sense of being in a solar system at all. They would see only the blackness of interstellar space and the distant, unchanging stars. The Oort cloud is thought to mark the practical boundary of the sun's gravitational influence. Beyond it, the gentle pull of the sun is no longer strong enough to hold onto objects. They would be more influenced by the gravity of passing stars or the overall gravitational field of the galaxy itself. The exact outer edge of the Oort cloud is not precisely known. It is a soft, gradual transition, not a sharp line. The solar system does not end at a wall. It simply fades, slowly and gently, into the interstellar medium, the thin gas and dust that fills the space between the stars. The sun's heliosphere, the bubble of solar wind that protects our system, also ends somewhere in this region, merging and mixing with the interstellar winds. The Oort cloud is the outermost layer, the final whisper of our home before it gives way to the vast, quiet spaces of the galaxy. There is a gentle, calming thought in all of this. The Oort cloud, this vast, unseen shell of icy fragments, is the source of some of the most beautiful and transient sights in our night sky. Comets, with their glowing heads and long, shimmering tails, are reminders that the solar system is not just a collection of planets on fixed orbits. It is a dynamic, interconnected whole, where the outermost reaches can send visitors inward, connecting the distant past with the fleeting present. A comet that graces our skies for a few weeks may have spent the last several million years drifting alone in the absolute cold and silence of the Oort cloud. It is a quiet, patient cycle, a slow breathing in and out over timescales that dwarf our own lives. As we float here, at the imagined edge of the Oort cloud, we have now traveled the full length of our solar system, from the sun at its heart to this distant, frozen shell. We have visited the rocky inner worlds, crossed the asteroid belt, marveled at the gas giants, drifted past the tilted ice giants, explored the frozen Kuiper Belt, and now we rest at the very edge, where the sun's hold is weakest and the interstellar dark begins. We are surrounded by silence, by cold, by a peace that has lasted for billions of years. The icy fragments of the Oort cloud drift around us, unseen, patient, holding within them the unchanged material of the solar system's birth. And out here, there is no rush, there is no hurry. There is only the slow, quiet turning of the galaxy and the faint, distant light of the sun, still holding us, gently, in its gravitational embrace. We will stay here for a moment, letting the stillness settle deep into our bones, before we take the final, soft step back to look at the whole quiet system one last time. And so we have arrived at the final, soft step of our journey. From here, at the farthest edge of the sun's quiet influence, we can turn and look back. We can let our gaze drift inward, past the Oort cloud, past the Kuiper Belt, past the planets, all the way to the warm, bright center of everything. And what we see, from this great distance, is not a collection of separate worlds, but one single, unified structure, a solar system, a calm, orderly neighborhood of space, held together by the quiet, steady pull of gravity, drifting as one through the vast, dark ocean of the Milky Way galaxy. Let us pull back very gently and see the whole system at once. At the center, of course, is the sun. It contains nearly all the mass, nearly all the energy, nearly all the light. It is the anchor, the heart, the reason everything else is here. Its gravity reaches out in all directions, an invisible web that holds every planet, every moon, every asteroid, every comet in its slow, predictable path. The sun is the steady drumbeat, the quiet metronome that sets the rhythm for the entire system. And around it, arranged like the concentric rings of an ancient tree, circle the planets. The four small, rocky inner worlds, huddled close to the warmth. Mercury, the tiny, airless one, swinging between searing heat and freezing cold. Venus, shrouded in thick clouds, spinning slowly backward. Earth, our own blue marble, with its single large moon and its vast, life-giving oceans. And Mars, the red desert world, with its ancient volcanoes, its deep canyons, and its quiet, open questions about water and life. Beyond Mars, we crossed the asteroid belt, that scattered field of rocky leftovers. A planet that never was, its materials stirred and prevented from gathering by the immense gravity of Jupiter. And then came the giants. Jupiter, the largest of them all, a swirling world of gas and storms, with its great red spot and its family of dozens of moons, including the icy Europa with its hidden ocean. Then Saturn, the pale golden planet, wrapped in its delicate, shimmering rings of ice, accompanied by Titan with its methane lakes and Enceladus with its quiet, spraying plumes. These two gas giants dominate the outer solar system, their gravity shaping everything around them, their presence a slow, heavy counterpoint to the small, rocky worlds inside. Farther still, we drifted past the ice giants. Uranus, tilted on its side, rolling around the sun, its pale blue-green color a whisper of the cold. And Neptune, the last of the planets, a deep, vivid blue, with the fastest winds ever recorded, and its captured moon Triton, a frozen world with active geysers, circling slowly backward. These are the 8 major worlds, the official planets, each one unique, each one following its own quiet path around the central fire. Beyond Neptune, we entered the Kuiper Belt, the wide, disc-shaped region of icy debris. Here we found Pluto, the small, complex world with its mountains of water ice, its plains of frozen nitrogen, and its large moon Charon, the two of them orbiting a shared point of gravity, a binary pair in the deep cold. We found other dwarf planets too, Eris, Haumea, Makemake, and countless smaller, unnamed objects, all of them leftover building blocks from the solar system's formation, preserved in the frozen dark. And finally, we arrived at the Oort cloud, the vast spherical shell of icy fragments that marks the practical boundary of the sun's influence. A region so distant that the sun is just another star, so vast that its objects are separated by millions of miles of empty space, so cold that all motion nearly ceases. The Oort cloud is the final whisper, the last faint echo of the solar system before it fades entirely into the interstellar medium. This is the structure of our home. A star, 8 planets, many moons, and countless smaller bodies, all arranged in a flat, orderly disk, nested inside a spherical shell of comets, drifting together through the galaxy. Now, as we hold this whole image in our mind, let us remember the one quality that defines it all: emptiness. The vast, almost incomprehensible emptiness between things. We touched on this at the very beginning, and it is worth holding again, softly, as we prepare to let go. The solar system is mostly empty space. If you could shrink the sun down to the size of a grapefruit, the Earth would be a tiny speck, the size of a grain of sand, orbiting about 50 feet away. Jupiter would be a marble, orbiting a few hundred feet away. Pluto would be a microscopic dot, nearly half a mile distant, and the Oort cloud would extend for hundreds of miles in every direction. The space between the objects is so vast, so overwhelmingly large, that the objects themselves are almost insignificant. The solar system is not a crowded, busy place. It is a quiet, sparse, peaceful neighborhood, where each world has room to move, where collisions are rare, where silence and stillness are the norm. The emptiness is not a void to be feared. It is a soft, dark blanket, wrapping each planet and moon and comet in its own private solitude. And in that emptiness, there is a profound kind of peace. There is no noise in space. Sound cannot travel through a vacuum. The great storms of Jupiter rage in absolute silence. The volcanoes of Io erupt without a whisper. The geysers of Enceladus spray their plumes into a soundless void. The entire drama of the solar system, the spinning planets, the falling comets, the fusing sun, all of it plays out in a perfect, unbroken quiet. The solar system is a silent movie, a slow, beautiful ballet performed without music, without applause, without any audience but the stars. And even now, after all we have explored, after all the worlds we have visited and the distances we have crossed, the map is not finished. It is a gentle, calming thought to hold as we end our journey. Even now, new small objects are still being found at the solar system's edges. New moons around the giant planets, new dwarf planets in the Kuiper Belt, new comets falling in from the Oort cloud. Our understanding of our own home is not complete, and it may never be. There is always more to find, more to learn, more quiet, distant worlds waiting to be noticed. The solar system is not a closed book. It is an open, ongoing story, a story that has been unfolding for 4.5 billion years and will continue to unfold for billions more. And that is perfectly all right. The not knowing is part of the calm. We do not need to have every answer. We can simply appreciate what we do know and rest in the quiet mystery of what we do not. So now, as we come to the very end of our tour, imagine yourself drifting very slowly, very gently, outward from the Oort cloud. The last icy fragments are falling behind you, one by one, their faint, frozen surfaces reflecting the distant light of the sun. The sun itself is now just a point of light, indistinguishable from the other stars. The solar system, that whole vast, orderly structure we have spent so long exploring, is now behind you, a tiny, warm memory in the endless dark. You are drifting into the interstellar space, the quiet between the stars. There is nothing around you but stillness, no sound, no motion, no rush, just the soft, eternal dark and the distant, steady glow of the Milky Way. There is nothing you need to remember from this journey, nothing you need to hold on to. The planets will keep spinning, the sun will keep shining, the comets will keep falling on their long, slow paths. The solar system does not need your attention to continue its quiet dance. It has been doing this for billions of years, and it will do it for billions more. You can let it all go. You can let the images fade, like clouds dissolving in a twilight sky. The sun, the rocky worlds, the gas giants, the ice giants, the frozen outer reaches, all of it can drift softly away, leaving only the stillness, only the quiet, only the deep, calm dark. You are floating now, weightless and free, past the last icy fragments of our home. There is nothing left to hold on to, and that is a gift. There is nothing left to do, and that is a peace. The journey is complete, the tour is over, and you are exactly where you need to be, drifting gently outward, into the stillness, into the quiet, into a deep and restful sleep.